Strathclyde, working in the field of S-block organometallic chemistry. Upon returning to Oviedo, he consolidated the academic career through competitive research programs, leading to the current position as Professor Titular de Universidad. Over the years, he has focused on sustainable synthesis, particularly involving transition metal catalysis and organolithium reagents in unconventional media, such as deep eutectic solvents, water, and glycerol. He was also awarded by the Spanish Royal Society of Chemistry the Young Scientist Prize and has been listed for 2 consecutive years among the top 2% most influential chemists in Spain by the Stanford University. So please, Joachim.
So thanks, Francesco, for your really kind introduction. And I will also like to thank the rest of the organization committee, Francesco, Daniela, Ana Rita, and also the scientific committee for giving me the chance to be here today to present you part of the chemistry that we are currently developing in our research group. It's a real privilege for me to have the chance to present you our chemistry. So during the last years in our research group, we are studying the application of both transition metal complexes or main group organometallic reagents in organic synthesis using what we call sustainable solvents. That's basically deep eutectic mixtures or water. In this sense, we have studied a variety of transition metal catalyzed organic transformations, working in most of the cases at room temperature in the presence of air. And very important, we do not need to use any halogen abstractor. We do not need to use bases or halogen abstractors. We are also studying in collaboration with a group of Professor Eva Evia at the University of Bern in Switzerland, and the group of Vito Capriati at the University of Bari here in Italy, the addition of highly polarized organometallic reagents into different unsaturated organic substrates, working again at room temperature in the presence of air and using protic deep eutectic solvents. We have a third line in the group, which is related with the use of acidic deep eutectic solvents as promoters in organic synthesis. For example, to promote the regio and stereoselective conversion of internal alkynes into the corresponding vinyl sulfides. And finally, we are also studying what we think is a very nice concept in catalysis, which is related with the design of hybrid one-pot tandem protocols, in which we try to put together different synthetic organic tools in the same reaction media. For example, transition metal catalysis and enzymes to obtain chiral amines or chiral alcohols. And this work has been done in collaboration with a spin-off company called Entrechem, and in the lab in Oviedo has been done by Dr. Nicolás Ríos Lombardia. So the first question that I think that I need to solve in this talk is what are these deep eutectic solvents and how they look like? So as we have seen in previous talks, deep eutectic solvents can be formed just by mixing together 2 or even 3 safe and cheap components, which are able to interact each other through hydrogen bonds to form a liquid eutectic mixture. One of the most commonly used components for the synthesis of these eutectic mixtures is choline chloride, which is a safe and non-toxic quaternary ammonium salt. In combination with different hydrogen bond donors, like, for example, urea, different organic acids, amines, or polyalcohols, choline chloride is able to form liquid eutectic mixtures. These mixtures gather several advantages as compared with traditional ionic liquids. For example, the low price, the chemical inert against water. Some of them, not all of them, are biodegradable, biocompatible, and non-toxic. And very important, they are very easy to synthesize. You only have to mix together the 2 components, so no problems with purification or waste disposal, and as you will see in this video. So let me check if I can. So that video was actually recorded by our PhD student, Marina Ramos. As you can see in the video, we start with two solids. That's urea on the left-hand side, that's choline chloride on the right-hand side. Melting points in both cases above 100 degrees. So you only have to mix together the two components. So no problem with moisture, no problem with air. We can work and we don't need to use a slime type techniques. Just put everything together in the vial. You add the stirrer, you close the stirrer, and you heat it. Only at 70, 80 degrees, which is a temperature far below the melting points. So you're using the heat basically not to melt the products, just to form the eutectic mixture, as you will see in a moment. So this is a fast video. It takes like half an hour or so, and you form a new liquid. You can see the formation of the eutectic mixture. And the beauty here is when you finish, you don't need to do any isolation, not any purification, just the final deep eutectic solvent that you can work like with other conventional box solvent. You measure volumes, you add into the reaction media. The only thing is that you can see is a bit more viscous than traditional box solvents. So after seeing this video, it's easy to understand why deep eutectic solvents have been already used as innocent, and I want to highlight here the word innocent, environmentally friendly reaction media in a variety of transformations that you have there. For example, we saw yesterday for the metal oxide dissolutions. However, in the lab, what we are trying to do is not use this solvent also as innocent, but also as promoters of organic synthesis. This is the first part of the talk. So the use of acidic deep eutectic solvents as promoters in organic synthesis. So the next question that you may have is how you can synthesize acidic deep eutectic solvents. And here, actually, the beauty again is you have two different routes. You can start with an acidic hydrogen bond acceptor, a Lewis acid. So basically, any transition metal salt that you can think of. Zinc chloride, for example, we have here. You can use iron chloride, tin chloride, or you can use also acidic hydrogen bond donors, typical carboxylic acids. So for example, you can use oxalic acid, you can use malonic acid or citric acid. And the beauty here is that you form a liquid with unique acidic properties that cannot be replicated in most of the cases by the components that you're using. So when we started with this project, there were a few examples in the use of acidic deep eutectic solvents in organic synthesis. We have this very nice idea by François Jérôme in France. They are using this Lewis acidic deep eutectic solvent based on iron for the synthesis of furans. And also you can use Bronsted acidic deep eutectic solvents, in this case based on tartaric acid, reported by Koenig for the synthesis of dihydropyrimidones. And here I would like to highlight the work done by our friend in Bari, you know him, Vito Capriati, who is using iron-based deep eutectic solvents for the synthesis of amides, sulfonyl amides, for the oxidation of secondary alcohols and even to promote the Ritter reaction. So after this general introduction, in the first part of the talk, I would like to show you how this iron-based deep eutectic solvent, this Lewis deep eutectic solvent, is extremely powerful and versatile synthetic organic tool, which can promote at least 3 different reactions. We're going to promote a Mayer-Schuster rearrangement, hydration of internal and terminal alkynes, and even the formation of carbon-carbon bonds. So let's start with the first part, the Mayer-Schuster rearrangement. So in our research group in Oviedo, several years ago, we reported the isomerization of propergelic alcohols, terminal ones in this case, using a traditional ionic liquid, PEMIN PF6. Working at 80 degrees, we need to use argon. The system can be recycled up to 5 consecutive runs. It's not bad, but we still need to use a rhenium catalyst. So what Nico in the lab found is that by using this iron-based deep eutectic solvent, now the reaction takes place at room temperature. And here I would like to draw your attention that this is one of the few examples in the literature which describe this reaction at room temperature. Moreover, the system now tolerates both internal and terminal alkynes, have very good yields. The system can be recycled with no problem. We do not need to use nitrogen or argon, like in the previous cases. We are just using iron, which is a cheap and easily available first raw metal when compared with rhenium. And also very important from a synthetic point of view, the reaction can be scaled up with no problem. And when these final products are solid, they crash down from the reaction media, so we don't need to use any solvent, just filtration for the isolation. So that's the first example. We have also done the activation of other carbon-carbon triple bonds, typically hydration of internal and terminal alkynes. And as you probably know, transition metal catalyzed, traditional hydration metal catalyzed hydration usually requires of high temperatures, methanol as co-solvent, acidic co-catalyst, the use of box solvents for the purification and isolation of the ketones, protecting atmosphere, and is usually based on expensive transition metals, gold, silver, palladium, or ruthenium. So again, what we found in the lab, in this case is Marina and Nico, they found that by using again the dibutyric solvent, now the reaction takes place in most of the cases under very mild reaction conditions. Moreover, we don't need to use any box solvent. Again, when these ketones are solid, they crash down from the reaction media. We work under air, no co-catalyst. The system can be recycled up to 8 runs, and we make our duty. So we make the calculations of the green matrix, and we have quite a very good bond. Apart from that, and from a synthetic organic point of view, I would like to highlight that the system tolerates a wide variety of functional groups. You can work with electrodonating groups, you can work with electron accepting ones, you can work with different substitutions, so it's a very versatile synthetic organic tool. The system also tolerates internal alkynes. However, here we have a different product. We form a 1,2-diketone, which comes from a formal hydration-oxidation reaction. So here we need higher temperatures, 110 degrees, and longer reaction times, but we can produce these very, very nice products. So what we know that's happening, basically the first step is the expected hydration, you form the ketone. Then you have alpha chlorination, this upper hydrolysis, you form the alcohol, oxidation, you have the ketone. And the good news here is you only need to use oxygen coming from air as co-oxidant. System recycled up to 3 times and very good yields. We were very glad to know that this work was selected as front cover in Chemistry European Journal. So all that I have shown you till now basically deals with the activation of carbon-carbon triple bonds. However, the same system is actually able to promote the formation of carbon-carbon bonds. So I'm going to give you a flavor of this project that we have just recently reported in Cancer Chair. So I have to say that here the conditions is 120 degrees, longer reaction times. However, the good news here again is that we can work under air. And from a synthetic point of view, we can use any electrophile that you want for the reaction. So you can use styrens, you can use benzylic alcohols, chlorides, acetates, or ethers. And also on the other side, we can use basically any nucleophile that we want. So arenes, polysubstituted arenes, or even those that contains heteroaromatic rings. The system works very, very good with activated substrates, what we call activated substrates, which are rich arenes, very good yields, very good rich selectivities, and moreover tolerates challenging arylation substrates. Basically, pure the activated arenes, we have moderate yields, but normally quite good regio selectivities. We can also work with the activated electrophiles, and the system tolerates, for example, naphthyl groups. We can work with heteroaromatic rings, alkyl groups, so again, very versatile. From a given chemistry point of view, it's important that we can scale up the reaction up to 10 millimoles. We can produce this very important product in chemical industry. And finally, the system can be recycled, in this case, up to 10 consecutive runs. And this is very nice, because when you make the reaction, you see that the reaction takes place, and when you finish at room temperature, you form this bilayer, basically. So that means that you just can take out the organic product from the chalk, and you can recycle the system without any box solvent. So all that I have shown you till now basically deals with the use of a Lewis acidic deputatic solvents in organic synthesis. In the second part of the talk, I would like to show you how Bronsted acidic deputatic solvents are the ideal candidates for the design of one-pot tandem protocols. For example, the hydrogenation and sulfonylation of internal alkynes, or this three-component reaction that takes place in a one-pot, one-step reaction. So actually, why is interesting the design of one-pot tandem protocols from an organic point of view? And this is basically because these one-pot tandem protocols, as we saw the other day also in a talk, they are emerging as alternative routes to classical multi-step processes because they minimize the chemical waste, they save both time and energy, and simplify practical aspects, as usually no isolation of intermediates is needed. So let's start with this first project, the hydrogenation and sulfonylation reaction. So you have seen this slide before. We know that this iron-based deputatic solvent can promote the formation of these 1,2 diketones. When we were studying the mechanism of this reaction, Gloria and Nico found the formation of this very interesting product. So we formed this vinyl chloride, which comes actually from a formal hydrochlorination reaction. This intermediate has been previously proposed when catalytic hydration of internal alkynes takes place with iron chloride. So we tried to isolate this product, but we were not able to do it. So we decided to move from a formal hydrochlorination reaction into a formal hydrogenation reaction just by using choline iodide as hydrogen source, as iodide source. And please go with me now back to your undergraduate students. So let's go back to the first year organic chemistry, if you remember. So in that course of organic chemistry, they will probably teach you that if you start with an internal and non-symmetrical alkyne and you want to add hydrogen iodide, you can have several products. The first couple of ones are the Markovnikov and the anti-Markovnikov products. And please remember that you, apart from these 2 regioisomers, you have also 2 stereoisomers. So that means that you have 4 products already. It's also quite well known that you can have the formation of molecular iodine as byproduct. So you can have direct addition to the double bond, to triple bond to form this product, sorry. And finally, you have an acid, so typically hydration. So you can have at least 6 products of the reaction. So we start by using an iron-based deputatic solvent containing choline iodide. As you can see in the slide, we basically observe only formation of this product. So direct addition of molecular iodine. We change the Lewis acid for zinc or for tin, and basically there's no reaction. So the take-home message from this slide is that the Lewis acidic deputatic solvents are not capable of promoting the hydrogenation. So imagine that you were with us in the lab, so the reaction is not working with the Lewis acid. What's the next thing that you will think of? So Lewis acid are not working, you just go for the Bronsted one. So that's what we did. So that's the beauty of the deputatic solvents. They are very tunable. So we just moved to Bronsted acidic deputatic solvents, still based in choline iodide as halogen source. And when we use malonic acid, we start to see the final product. And the beauty here is as soon as you increase the strength of the acid, if you move from malonic acid into camphor sulfonic acid or torsalic acid, we can have better yields. However, when you use, for example, methensulfonic acid, you basically have hydration. And the best partner here is paratoluene sulfonic acid. We have better yields and we have quite good stereoselectivity. So we decided to keep this paratoluene sulfonic acid, but we want to improve the yield. So we know already that the best partner is paratol and sulfonic acid. What else you can change? You can change the source of the iodide. So let's change choline iodide by other quaternary ammonium salts or phosphorium salts. And here, as you can see in the slide, we have a problem because we promote the synthesis of the anti-Markovnikov one. The last thing that we did actually was to study the amount of the dibutyric solvent that we are using. And when we reduce from 8 equivalents into just 1.5 or 2 equivalents, we have very good yields or quite good yields and very good stereoselectivity. But still the reaction takes quite long, 20 hours. So we decided to increase the temperature up to 80 degrees. And now these are our conditions. So just 6 hours of reaction. So under these optimized reaction conditions, we extend our studies to a variety of internal alkynes. What we did first is to keep constant this phenyl group here. So this blue dot here, always phenyl group, and we changed the green one. The system tolerates methyl groups, as you have seen before, phenyl groups, but the best yields are always obtained when we use electro-withdrawing groups, like, for example, nitriles, for example, carboxylic acids, esters, or amides. Then we just study the other partner of the reaction. So we keep constant this amide group, and we just change the nature of the aromatic ring. The system tolerates electro-withdrawing, electrodonating groups, heteroaromatic rings, aliphatic ones, and naphthyl ones. So once we have solved the hydrogenation reaction, remember we want to design a one-pot tandem protocol. So we decided to study a sulfonylation. This is a one-pot, two-step reaction, which means that we first promoted the hydrogenation, and when the reaction is finished, we add the thiol in the reaction media. Again, we make quite a lot of study of the scope of the reaction. We start our studies by using a thiol, always thiophenol that you have here. We keep constant this phenyl group, and we just change the nature of the electro-withdrawing group. And the system works quite well. We next keep constant the thiophenol group, we keep constant the amide group, and we change the aromatic ring here. And again, as you have seen before, no problems with different substituents. And very interesting, the reaction tolerates also a wide variety of thiols. You can work with other aromatic thiols, aliphatic thiols, containing heteroaromatic rings, like pyridines, for example, furans. And very important, is capable of working with amino acids, like cysteines, which are very, very challenging products in this reaction, and also with the selenium derivatives. Most of the cases, good yields and very good stereoselectivity. And we were very glad that this work was selected as front cover in advanced synthesis and catalysis. So let's keep on going with the use of bronze acidic butyric solvents for one-pot tandem transformations. And I just want to give you also a flavor of this reaction. And I would like to state clear from the beginning that this is a one-pot, one-step reaction, which means that the three components are together from the very beginning of the reaction. And the three reactions that you're going to see in a moment are promoted by the same organic synthetic tool. So basically, we put, as I was saying, the terminal alkyne, the aldehyde, and the nucleophile all together in the presence of the acidic dibutyric solvent. The first reaction that it takes place, as expected, is the hydration. So you can form the ketone. You have an aldehyde in the reaction media. So you have the condensation. You form the alpha beta unsaturated carbonyl compound, and then you have two nucleophiles that you can use to form the corresponding gamma ketophosphine oxides or gamma ketosulfones. Very good yields again. Final products are solid, which means that they crash down from the reaction media. You do not need to use any bulk solvent in the isolation. The system can be recycled up to 5 consecutive runs, and we have quite a very good value of the E factor. So all that I have showed you till now in this second part of the talk is related with one-pot tandem transformations in which we use the same synthetic organic tool during all the process. So for example, here is only this dibutyric solvent who promotes the three reactions. In the third part of the talk, I would like to show you our efforts in the design of hybrid one-pot tandem protocols. The difference here is now that we are using different synthetic organic tools in the same reaction media. For example, in this case, you have ruthenium catalyst. This is the isomerization of allylic alcohols. Mixtures, racemic mixtures of allylic alcohols can be converted into prochiral ketones, and then gamma transaminases or alcohol dehydrogenases can produce the corresponding chiral alcohols or chiral amines. Okay, so a bit of introduction here. So you have seen this slide before. This is why it's interesting, the design of one-pot tandem protocols. However, I would like to highlight that the design of hybrid one-pot tandem protocols is one of the most difficult challenges, in our modest opinion, that you can have in your head, because you need to have different synthetic organic tools in the same reaction media. Transition metal catalysis, enzymes, organocatalysis, and main group chemistry. And please remember that each of these organometallic or organic tools requires of different solvents, different concentrations, different co-catalysts, which means that you can have reciprocal poisoning between the two systems. So when we start with this project back in 2017 or so, we ask ourselves the question that you have here in the slide. Are diputhatic solvents or water the solvent of choice for the combination of main group chemistry? So organolithium reagents basically with transition metal catalysis, with organocatalysis, or even with enzymes. And of course, the answer is yes, because it's not, I will not be here speaking today about this chemistry. So all this chemistry of organolithium reagents comes from a joint paper that we reported with Eva in 2014, in which actually we studied the addition of polar organometallic reagents under bench-type reaction conditions. So room temperature, presence of air, and protic solvents. And if you dig a bit, these are the conditions for other organic synthetic tools. Basically, for example, for enzymes or for transition metals. So we have quite an open ground to work here. Moreover, by using these bench-type reaction conditions, we have better yields and better selectivities. How we can explain this chemistry? So at the time, we proposed the formation of highly nucleophilic and anionic magnesiates or lithiates, which are more nucleophilic than the starting neutral species, which means that the choline chloride here has a double role. For one side is the hydrogen bond acceptor that you need for the synthesis of the protected mixture, but also is the halide source that you need for the formation of this anionic species. So we propose some sort of kinetic activation similar to that reported for turbo-Grignard reagents. Okay, so that's the starting point. So the first hybrid combination I'm going to show you is the one you have on the screen, done with Vito in Bari. It's the combination of main group chemistry and transition metal catalysis. So during the last years in the group, we have reported a variety of bisallyl ruthenium-4 complexes as extremely powerful tools to promote the isomerization of racemic allylic alcohols into saturated ketones. Working diputhatic solvents, no co-catalyst, so quite nice conditions. I have shown you already that we can promote the chemioselective addition of organolithium reagents into ketones, basically in the same conditions. So we wondered ourselves if it was possible to combine these two reactions in the same flask, in the same pot, and why not use highly efficient ruthenium catalyst to convert allylic alcohols into ketones and organolithium reagents to convert these ketones into the corresponding tertiary alcohol. And actually the reaction works pretty well when we use the eutectic mixture choline chloride glycerol as solvent. So we are able to convert allylic alcohols into saturated tertiary alcohols in good yields, good chemoselectivity, and the take-home message here is that we do not need to isolate any intermediate, which means that the organolithium reagent is capable of working with the ketone even in the conditions imposed by the ruthenium catalyst. So that's the first hybrid combination. We have also reported the combination of organocatalysis and main group chemistry. And here, our colleagues in Entrochem told us that it was possible to promote this very simple reaction. So this is an organocatalytic oxidation of secondary alcohols into ketones, working with this Azado system, water, room temperature, presence of air. Vito showed before that it's possible to add organolithium reagents into ketones, again, water, room temperature. So we have actually two tools working in the same conditions. So why don't we just use organocatalysis to convert secondary alcohols into ketones and organolithium reagents to convert these ketones into the corresponding tertiary alcohol? And the reaction works again pretty well. We use water absorbent, you can work under air. The system has quite good scope for organolithium reagents. We can work with aliphatic one, with aromatic ones. Best yields, of course, are obtained with aliphatic or linear ones than branch ones. And there's no reaction actually with linear reagents. So let's move now to the third and last combination, is the combination of enzymes and organolithium reagents. So again, here, our colleagues in Entrochem told us that it was possible to replicate the same reaction, but moving from organocatalysis to biocatalysis. You can use a copper-based enzyme, which is called lacases, that comes in termeters versicolor in the presence of tempo to promote the same oxidation reaction. You have seen this before. It's possible to add organolithium reagents into ketones, so we can probably do this reaction. So we start with a secondary alcohol, biocatalysis, we make the ketone, and then we add the organolithium reagent. The problem that we have here is that for the addition reaction, we cannot use just pure water. We need to use a biphasic system, water and ether, which actually allow us to work with partially water-soluble ketones, like, for example, acetophenones that we cannot use in the past. We have quite a good scope of organolithium reagents. Very important, we do not need to isolate the ketone. So this is quite interesting. The organolithium reagent is capable of working in the presence of tempo. It was reported this reaction before. However, here, the organolithium reagent can work in the presence of the lacase, oxygen, tempo, with no problem. And we have very good chemioselectivity. Finally, you can also the same enzyme to promote other reactions. For example, you can promote the biodeoxymation. So you can also form ketones starting from oximes. So basically, the same reaction. You start with an oxime, transmertes lacase makes the work. You form the aromatic, the ketone, and then you can have the organolithium reagent. And this work, again, was selected as inside copper in OBC. So all that I have shown you till now basically follows the same step, the same pathway. You use the enzyme basically to produce an oxidation, you form the ketone, and then you use an organolithium reagent to promote the synthesis of the tertiary alcohol. But remember, I'm an organometallic chemist by formation. So we say, why don't we just try to do the reaction the other way around? So why don't we use organolithium reagents to try to synthesize prochiral ketones and then use enzymes to convert these prochiral ketones into the final biocatalysis? And at that time, there was no precedent for this kind of reactions. So the first thing that you need is an organolithium-mediated reaction that promotes the synthesis of prochiral ketones. And we were very lucky because we already have that reaction in the lab. We reported the addition of organolithium reagents into nitriles working at room temperature presence of air and under neat conditions. What's the meaning of neat conditions? That means that we just take the solution from the commercial bottle of butyl lithium and we just add it directly to the reaction media. Then we make hydrolysis, we convert the imine into the prochiral ketone. Very good yields, no problems at all. In the other side, ketone reductases have been promoted, are extremely powerful tools for the conversion of prochiral ketones into the corresponding chiral amines. So again, we wondered if we can put this reaction together in the same reaction media. So let's start with aromatic nitriles. Let's form imines, hydrolysis, ketones, and then reduction. So you can convert aromatic nitriles into chiral secondary alcohols. And this work was done in collaboration with a group of Professor Vicente Gotor Fernandez and the late Ivan Lavandera at the University of Oviedo in Spain. So what Gloria and Nico did here first was to study the first reaction, the addition of the raw lithium reagent, and works quite well. We work with methyl lithium. We add methyl lithium into a variety of aromatic nitriles. We form the imine here, and very important, this part here. For the hydrolysis, we are using the reaction media needed for the second step, for the bioreduction, which implies the use of this Tris buffer. By doing this reaction, you can convert nitriles into the corresponding ketones. And here it's very important to mention that we never observe double addition. Remember that ketones are more reactive than nitriles, again, methyl lithium. However, we never observe the formation of the corresponding alcohol. So let's make a break here for a second. So let's leave hybrid one-pot tandem reactions. As I told you before, I'm an organometallic mixed chemistry by formation. So in the lab, when a reaction takes place with organolithium reagents, what's the next thing that you will think that we do in the lab? Just move to Grigners. So nothing very clever. And actually nothing was working. But however, just at the last attempt, we found this reaction. It's the same conditions, where the beauty here is this magic allyl magnesium bromide. So we make the addition, hydrolysis in this case with ammonium chloride. This was in collaboration with a group of Fernando Carrillo Hermosilla at the Universidad de Castilla-La Mancha in Spain. And we observed the formation of this very, very nice product. It's a tetrahydropyridine. However, as probably has also passed sometimes to you, someone else has reported this chemistry before. It was a great Erker, 1995. However, our input here is that Erker proposed the participation of this magnesium, this Lewis acid. However, in collaboration with a group of Professor Israel Fernandez at the Universidad Complutense de Madrid, we found that the reaction actually is promoted by a Bronsted acid, by the protons. So we think, okay, if the reaction is promoted by the hydrolytic reaction media, what is going to happen if we change this media? So instead of using acidic media, let's see what happens if you have protons. Let's see what happens if you have basic hydrolysis, which is not so common, but just using an ammonia solution and change completely. In this case, we form this amino ketone. So the same intermediate, two different products, just depending on the hydrolytic reaction media. And as far as I'm concerned, this is one of the few examples in the literature which describe this behavior. So how we can form this product? So basically, again, this is a proposal. This is not a mechanistic study. This is a proposal. So you form the imine, enamine, sigmatropic rearrangement. You have an alpha, beta, imine, hydrolysis, 1,4 addition. So the take-home message here is when you make your organometallic reactions, check different hydrolytic medias. And this work was selected. We're very happy to see that it was selected as inside cover in chemical science. So I'm just taking out my organometallic dress and I'm just going back to one-pot tandem transformations. Remember that we want to do this to convert nitriles into alcohols, chiral alcohols. We have already shown you this. So it's not a problem to produce these prochiral ketones. So we need to parameterize the second reaction. And again, here there's a huge amount of work in this slide. We're very happy to find that there are 3 different enzymes that can promote this bioreduction, which means that you can synthesize both the R and the S enantiomer. That's a beauty thing of biochemistry, of bioorganic reactions. We need to optimize a lot the concentration of the substrate, the enzyme loading, the 2-propanol, and also the presence of ether, because remember that this is the commercial solution, so it contains ether. So quite a lot of work by Gloria and Nico. And finally, we found quite good, that's this one, sorry. So basically, with the best results in hand, we can have very good conversion and excellent enantiomeric access for both enantiomers, for the R and for the S. So we were very happy to find that we can convert in a one-pot, 2-step reactions, aromatic nitriles into the corresponding chiral alcohols with very good yield and with excellent enantiomeric access for both enantiomers. which is quite a tricky reaction. And the work again was selected as a front cover in Advanced Synthesis and Catalysis. And before finishing, because I'm running out of time, just a very, very small flavor of other kind of project that we are working. We are very interested in the use of choline chloride, not only as a component of the eutectic mixture, but also as a possible organocatalyst. So we know that we can promote insertion of CS2 into other molecules. So for example, it can promote the insertion of CS2 into epoxides. Again, very, very nice. It's one of the beauties one that I have, I guess. It was reported in CanCom, and very recently can also promote the insertion of CS2 into nitrones. This is a named reaction. This reaction has never been reported before as far as we are concerned. So as a take-home messages, and I'm finishing here, so I hope that I have been able to convince you that this iron-based diputactic solvent is extremely powerful and versatile synthetic tool in organic synthesis, that bronze acidic diputactic solvents based on paratol and sulfonic acid are the ideal candidates for the design of one-pot standard protocols. And if you want to design hybrid one-pot standard protocols, water and diputactic solvents are the answer. And just the most important part of the talk, I would like to acknowledge the work done by our superb students, Marina, Marcos, Gloria, the other senior members of the group, Nicolas, Sergio, and Alejandro, our collaborators, most of them here in Italy. I'm very grateful to Italy because they have been great with me. The people who pays the bills, and of course the rest of the group in Oviedo, and of course to all of you for your really kind attention. Thank you.
Thank you very much, Joaquin, for your very interesting and clear lecture. We have time for questions.
Thank you very much. Very interesting. A lot of results and very selective catalyst. One small question about the iron system. You've shown that you can recycle it almost infinite, so 20 times. And just separating the organic layer from. And what about the content of iron into this organic layer? You have ever found?
That's a very good question. So what we did normally is in most of the cases, we still have like a bit of a yellow color in the final products. They remember there are organic products that are white. So what we did basically is we only need to add water. You can just, so you do the filtration. If you see that the product has still some content of iron that you see by naked eye because you see like a traces of orange thing. This diputactic solvent is soluble in water and you break them apart. So the two components just dissolve in water and you can have the final products. I mean, we have never done ICP, MS studies to see what is the content of iron, but I can tell you that just by washing with water, you can just take the other byproduct, or not the byproduct, I mean the promoter of the reaction mixture.
And
other questions?
Another curiosity about the last system, the enzyme, did they survive the first condition of, it can be recycled? No, I think.
I mean, this is something, you just have a look, we have two different ways of doing it. We can have the enzyme and that the organolithium reagent, and you can make it also the other way around. So in both cases, we can not reuse the enzyme. However, we are now in a collaboration with a group in the Basque Country that they are capable to produce what is called self-sufficient hetero systems, in which you have the enzyme, that you have it in a polymer, and you also have the cofactor. So it's something that we will try to do. So maybe when we finish, you can have like a, I don't know how it's called in English, so like a C18, where you have the enzyme. We will try to pass through the reaction and see which can do it several times. But remember that in most of the cases, once the organolithium reaction is finished, you only have lithium hydroxide. So you don't have any other salt. And what we have seen before is sometimes the co-solvent that you're using, like for example, ether, can denaturalize the enzyme. However, if you just leave the reaction open to air, the ether just goes away. Okay.
We have time for one more question. If not, I have at least 5 questions, so I will choose only one. I think it is possible to prepare chiral diprotectic solvents with.
Very good question.
Okay, is it possible to employ the chiral solvent?
That's a very good question, Francesco. We have tried and tried and tried. So you think the components, choline chloride can be replaced probably for amino acids, so like proline or whatever. In our case, we have never seen an induction, and I think it's because the component of the diprotectic solvent, the proline, is so happy doing things. You are actually like just
Neutralizing the chirality.
No. It's just in a super intense interaction with the other member of the diprotectic solvent, which I think is not possible to just transmit the chiral information because, and also remember that for chiral information, you need quite a solid pocket. And these are only intermolecular reactions. It's not a proper covalent pocket.
The rigidity.
So I have tried that because we produce secondary alcohols. B2 has also tried. There are some examples, but in our case, it's quite difficult. But that will be very nice because you can transmit chiral information, for example, with proline, or most of the products are actually coming from nature resources, so you can have a very cheap source of chirality. That's a very good question.
Thank you very much. So let's thank again Joaquin for this nice lecture. Next speaker is Morena Nocchetti. Morena is professor of general and inorganic chemistry at the University of Perugia, where she got both her degree and PhD in chemistry. Her scientific research addresses the studies of bi- and three-dimensional materials, such as hydrotalcides, zirconium phosphates and phosphonates, and hydroxyapatites. She has focused on the functionalization of these materials with chromophores, jugs, and metallic nanoparticles for application in a variety of fields, including catalysis, photocatalysis, cultural heritage preservation, and biomedicine. Please, Morena.
Good morning to everyone, and thanks, Chairman, for the kind introduction. First of all, I'd like to thank the scientific and the organizing committee to give me the possibility to share with you my contribution on the development on layer double hydroxide. Here there is the presentation outline, and this talk will provide an overview on the synthetic method to prepare LDH, and also the possibility to combine LDH with different materials with different dimensionalities. So the LDH are layered materials. Each layer is built up by the concatenation through the edges of octahedra, the center of which is occupied by bivalent and trivalent metal cations, and the vertices by hydroxyl ion. The presence of the trivalent metal introduces positive charges on the layers that are balanced by an ion located into the interlayer region. It's possible to obtain a large variety of these materials by introducing during the synthesis different bivalent and trivalent metal cations, and also using more than one of these cations, and also to turn the crystal morphology and size. During the post-synthesis procedures such as intercalation chemistry, it's possible to introduce different anions into the interlayer region, and they can be combined with other material to obtain hierarchical structures. So about the synthesis in our laboratory, we developed several methods. Each of them have some advantages in terms of morphology and crystal size. The first method is known as urea method, and foresee the use of urea as precipitant, reactant. In particular, we induce the hydrolysis of the urea that brings to the formation of ammonium carbonate that brings the pH at 9. That is a pH suitable to precipitate a lot of metal hydroxide. In this way, a small degree of supersaturation is achieved, so we obtain a large particle size in a micrometer dimension with high crystallinity. It's possible to obtain a lot of LDH by combining the metal that I show in this table. The only limitation is related to the ionic radius, that it should be suitable to be accommodated in an octahedral cavity. By finally adjusting the synthetic parameters, it's also possible to control the morphology of these micrometer crystals. So we obtain flower-like particles, sand rose aggregates, or hexagonal platelets with different also anion into the interlayer region in the order nitrate, carbonate, or chloride. In some application, it's important also to have nanoparticles. So LDH nanocrystals were prepared by using a double microemulsion technique, water in oil. In this case, the aqueous solution of the metal nitrate salt and the ammonia, that is in this case the precipitant agent, is contained in the swimming pool of micelle of two different microemulsion. When these are mixed, all the micelle are merged and the water solution mixed. So the LDH precipitated and into the confined environment of the micellar. The LDH obtained by this method are in form of stable colloidal dispersion and have diameters that range from 120 to 7 nanometers, depending on the metal present in the materials. With this method, we are also able to prepare photoluminescent LDH by solubilizing, introducing some amount of lanthanide anion in the brucitic sheet of these materials, despite the high ionic radius and coordination number of these cations. In a work edited by Professor Macchioni, we are also able to insert iridium into the layer, and with a deep structural investigation, we found that iridium is octahedrically coordinated with 4 hydroxyl ion and 2 chloride. These materials are showed a very good performances as catalysts for water oxidation. Recently, we prepare nano LDH containing antimicrobial metal such as gallium, zinc, and copper, and their antimicrobial activity was tested against this strain. All show a good MIC, so a good low MIC value, so a good antimicrobial activity, and the best one is the magnesium, copper, aluminum, according to the smaller particle. Indeed, the dimension of the particles affect the release of active metal in the culture medium of bacterial, and the smaller are the particles, higher is the release. To investigate the activity of the LDH on strains, CM micrographs were collected before and after LDH treatment. And we can see that the inorganic particle causes a modification of the cell wall, such as roughness, invagination, and also causes a defective cell division process, as we can see for the Candida albicans. In view to apply this LDH at industrial level, it's very important to develop green and scalable synthetic method. So we try to synthesize these materials with ultrasound assisted synthesis and ball mill synthesis. We prepare a lot of LDH with this combination of metal, but here I want to show you only the case of the iron-based LDH, because with this LDH we use this LDH as a catalyst precursor for both classical and CO2 Fischer-Tropsch synthesis for the production of hydrocarbons. The materials were designed in this way. This is the nominal composition. So beside iron, we introduced magnesium, copper, and they were prepared, as I said, by ultrasound and ball mill technique. The particles obtained are in the nanometer range, and before the catalysis, this compound was impregnated with potassium and activated in the catalytic reactor with the C gas at 350 degrees. After the activation, the formation of the active phases for Fischer-Tropsch were found, such as iron carbide and iron-based spinel. About the catalytic results, we can see that they promote a very good CO conversion and the CO2 conversion in the classical and CO2-based Fischer-Tropsch. The conversion increase with the temperature in both cases. And as for hydrocarbon selectivity, the ball mill one is more selective towards the light hydrocarbons. The ultrasound one is show high selectivity towards the EV cuts at low temperature. Now, it's possible to confer additional properties to LDH by combining them, for example, with zero-dimensional nanospecies such as silver-based nanoparticles. So, in this context, nanoparticles, silver on silver chloride, immobilized on LDH, were prepared. Were prepared by a two-step synthesis. In the first step, to a dispersion of LDH in chloride form with hexagonal platelet morphology, was added a solution of silver nitrate. The chloride acts as nucleating seeds for the silver chloride. So we have the precipitation of this salt and in the form of nanoparticles, as we can see from these CM images, in which it's possible to observe the surface of LDH completely covered from these particles. After that, the composite was submitted to a reduction, and the silver chloride was partially reduced to silver, metallic silver, and the formation of these particles are visible again in the electron microscopy. By electron microscopy, there is the appearance of this small population of particles that is ascribable to silver with a dimension of about 10 nanometers. It is well known that silver have a very good antimicrobial activity, and that LDH prepared with the right choice of the metal is biocompatible. So this material can be designed, can be used as biomaterials, and was of interest to check, to study the antimicrobial activity. The antimicrobial activity was studied against this strain and this yield, and the MIC value are very, very low, so testing the high activity, activity that can be due to the ability of the materials to release silver over the time in the culture medium of bacterial. It's also known that silver chloride system is a photocatalyst, so it was of interest to check the its photocatalytic activity after the mobilization on LDH. To do this, the photodegradation of rhodamine model dye was studied. The results are reported in this table and are compared with the pure silver chloride. The performance was expressed as a lifetime of rhodamine, and we can see that the catalyst supported show very good performances and works better than the pure silver chloride. It's possible to study also the ability to work in different run, and at the catalysts are effective also until the third run, even improving their activity. To get some insight on the photodegradation mechanism, the experiments were performed in the presence of radical scavengers, and we can see that in considering the percentage of dye decolorization, we can see that the photocatalysis was dramatically suppressed in the presence of benzoquinone, suggesting that the main species involved in the mechanism is the superoxide radical anions, and that the mechanism is dye photosensitized. The production of ROS also can work in synergy with the silver cations in improve the antimicrobial activity of these compounds. So we study by the time kill curves against Escherichia coli the activity of this compound, and we can observe that after 60 minutes of irradiation, the number of live cells decreases considerable due to this activity of ROS and silver cation. It's possible, moreover, to combine LDH with monodimensional materials such as lavisite. This composite was used to immobilize extract natural for food packaging application. Briefly, alloysite is aluminosilicate clay minerals with tubular structure, and the outer layer is made of silica, so they can have negative charges in the neutral environment. The alloysite was used as support for LDH, so LDH was precipitated on these materials by mechanochemical technique. And the formation of LDH was confirmed by X-ray powder diffraction and infrared spectroscopy. And we can observe the formation of LDH also by CM images. Here there is the morphology of alloysite that is constituted by nanotubes with smooth surface. After the LDH precipitation, this nanotube appears completely covered of LDH nanoplatelet. So this composite was used to support an natural extract obtained from the skin of red onion. It is the composition of this extract show the presence of isoquercetin and cyanidin that have antioxidant properties, and the cyanidin is the molecules that confer color to the extract, and its color is pH responsive. When the extract is grinded with alloysite LDH, its color turns to green due to the formation of the chinoidal base that interact with LDH. And this composite was used as a filler of polymer such as potato starch to obtain a green film. This film can change color, turns to pink in acidic environment, and it is able to come back when exposed in basic environment. So these films were proposed for smart packaging application due to their properties. They show antioxidant properties came from the isoquercetin cyanidin, and also they are able to act as a sensor of pH variation during the food spoilage. Finally, LDH has been combined with three-dimensional materials such as hydroxyapatite. In this case, the combination was performed in order to prepare osteogenic and antibacterial materials. This combination aimed at the preparation of biocompatible reactive interfaces for titanium-based prostheses. Titanium prostheses are subjected to infection that are very difficult to eradicate by antibiotic treatment due to the antibiotic resistance of the bacteria. So the implant fail, and the only solution, the solution to resolve this infection is the removal of the implant. It's important to develop biomaterials able to fight the bacterial, the infection, and in the same time to enhance osteogenesis, so to generate an overgrowth of the cell host, the host cell. To do this, we synthesize an LDH containing zinc and gallium that have oxo-inductive antibacterial properties. And we consider hydroxyapatite, that is a calcium phosphate that constitutes human bonds and have excellent biocompatibility and bioactivity, and also enhance osteogenesis. To do this, the hydroxyapatite was precipitated in the presence of LDH exchanged with dihydrogen phosphate. The structural investigation showed that during the precipitation, some zinc eluted from LDH and replaced calcium in the hydroxyapatite with the formation of a zinc-rich hydroxyapatite. The composite obtained were characterized by different techniques. Here I want to show you the CM images of the composite that is clearly constituted by the LDH crystal covered with flake-like crystals ascribable to hydroxyapatite. This composite show very good bioactivity, that is the ability to induce the formation of new hydroxyapatite when the materials is soaked in simulated void fluid. And we can see that after having recovered this composite, it is completely recovered by nanometric hydroxyapatite crystals. About the biological characterization, we can observe that LDH and the relative composite have a good antimicrobial activity against Staphylococcus aureus when is present gallium, also against Pseudomonas aeruginosa. They show also a good antibiofilm activity, exert a certain cytotoxicity on the human osteoblast, but a concentration higher than MIC. And about the human osteoblast proliferation, we can see that pure LDH show a decrease of the proliferation because a little degree of toxicity, while when the LDH is covered with hydroxyapatite, the osteoblast proliferation is promoted. So in this case, in this particular case, we are able to obtain a material with two functionalities. One is the antimicrobial activity, the other is the promotion of osteoblast proliferation. Then in conclusion, we can have seen that the composition morphology of LDH can be effectively tanned by choosing appropriate synthetic method. The reactivity of LDH can be exploited by modifying its surface with an ion able to induce the precipitation of specific materials, and also it's possible prepare LDH containing core shell structure materials, as we have seen in the case of halloysite. And obviously, new strategy can be explored to prepare a composite with LDH, such as exfoliation and reaggregation of this material in the presence of other systems. And at present, while a lot of research has been conducted on LDH materials, there is still much work to be done to fully develop its potential application. So let me thank my colleague of the Laboratorio di Chimica Inorganica, University of Perugia, the Professor Donatella Pietrella for the biological study, and Professor Carlo Pirola, Dr. Arian Grainka of Milano University for the Fischer-Tropsch catalysis, and all of you for the kind attention.
Thank you very much, Morena, for your nice presentation. We have time for questions. Silvia.
Thank you for the very interesting talk. I was curious about the mechanism of action of LDH. Do they act just only as a reservoir of active of active metals, or do they have a specific mechanism themselves? For example, they can act as a carrier of metal inside the cell, or other mechanisms, surface drive.
Excuse me, I understand the growth of LDH during the synthesis.
No, I was curious about the mechanism of action of LDH of your materials against bacteria.
Ah, okay. Thank you. The LDH exert antimicrobial activity thanks the presence of antimicrobial metal. Some metal have antimicrobial activity such as zinc, copper, and gallium, and in particular, gallium seems to work as a Trojan horse in the it have a number of sedation 3+, and it's able to mimic the behavior of iron, but it is not able to reduce to 2+. So, for example, in the case of Pseudomonas aeruginosa, the interaction of gallium with siderophore protein are the key of its antimicrobial activity. Perhaps also due the positive charge of the layer of LDH, they can interact with the negative surface of the bacteria. So also this interaction can causes the death of the cell. Moreover, when there is a silver, is also silver that act as antimicrobial because it can produce, as we can see, ROS, and also interact with the DNA, causes damage on the cell wall, and so on.
Okay, I think that we can thank again Morena because we are ready for the coffee break in order to be on time. I thank Joachim and Morena for the very nice presentation, and see you in a half hour.
45 minuti. Abbiamo un altro minuto. Good morning. Welcome to this new session that is dedicated to applied bioinorganics. The first speaker today is Riccardo Bonsignore from the University of Palermo. The title of his presentation is From Coordination Chemistry to Cancer Cells, Unveiling ROS-Mediated Cytotoxicity in a Redox-Active Copper-2 Schiff-Base Complex. Please, Riccardo. Vuoi provare con quello o preferisci muoverti? Come preferisci tu? Se ci puoi muovere il gelato.
Scusami.
Il contatore bisogna tenere premuto questo. Avanti e dietro.
Hi, morning everyone. Lovely to see you all. Apologies for the very long title. So I know it takes basically days to read it out. What I'm going to try to do today is just showing you how we moved from a target to exploit the unique properties of metal compounds. So first and foremost, anytime I try to define myself and I try to give a category to my research, I always say that I am a bioinorganic medicinal chemist, which is a very tricky way to say, because we don't really have too many metal compounds in clinics. Nevertheless, as I was saying, I'm really fond of metallodrugs. And the reason is that I believe that metallodrugs have unique properties that can be explored to better interact with the biological targets. They have a tunable geometry, they have peculiar electronic properties which can be fine-tuned to achieve a proper interaction with the biological targets, but at the same time, they can also catalyze unique reactivities, including cross-couplings reactions, but also redox reaction within the cellular environment. And this is great from my perspective. But if you have a close look to the amount of drugs that contains metals and that were marketed by either the EU or the FDA, well, you immediately spot that the figures are not so high. We are talking about few drugs containing metals. Besides, if you also exclude the drugs that contains iron, which is used as a dietary supplement, or even bismuth, which we know is used for antibiotic applications, the most of these drugs are containing platinum, which, as all we know, made basically the fortune of our field, because upon its discovery as an anti-cancer treatment, we had a huge boost in the research of metal compounds for medicinal chemistry application. Nevertheless, it also made the bad luck of the field, because cisplatin and all the related compounds have several side effects due to the lack of selectivity. And that's the reason why some of us didn't decide to disregard the metal compounds as potential medical application, but we started thinking of using these compounds for much more cancer-targeted therapies, much more cancer-targeted targets. And one of these was actually the G-quadruplex, which in the last 20 years have become quite relevant in the seek for an anti-cancer treatment. So G-quadruplexes are non-canonical secondary structures of the polynucleotide, which have been found in guanine-rich sequences, including promoter of oncogenes and telomeres, and therefore they've been associated with the development and progression of cancer. That is the reason why we've been thinking that the selective stabilization of G-quadruplex can become a powerful arsenal, powerful tool to hit a cancerous cell. At this point in time, as a group, we started around 2014, and as a group, as I was saying, we started working on metal-based compounds that could actually interact with this secondary structure. They are flat, planar, aromatic moieties, which can basically fit in the quartets of the G-quadruplexes. And so we started with these three complexes of nickel, copper, and zinc of a Sandhafen ligand, and we discovered that these were potent G-quadruplex binders, but more importantly, they were potent G-quadruplex stabilizers. And as we are curious, likely, I would say, we started playing around with this molecule. So we started modifying the NN bridge, introducing different moieties. We also started modifying the side chains, introducing aromatic moieties. And if you want to know more about the amidazole-based compounds, please cope with us a little bit, because our postdoc, Luisa, will be talking about that in a couple of minutes. But what was really striking to us was the fact that no one before has ever thought to modify the not colored part of the molecule so far. So we started thinking, what would it happen if we were to move from an N2O2 coordinating system to an N4? Or better to say, what would it happen if we move from a 6-member ring to a 5-member one? And the results was really striking. In 2021, we discovered that this little change in the molecule basically completely changed the trend of interaction with the G-quadruplexes. So we discovered that for the first time, the better G-quadruplex binder was actually the copper one. But nevertheless, this compound was not stabilizing the G-quadruplex, so it was not useful for our purpose. Yet, the fact that copper was winning over the other metals was something that triggered a little bit our interest, because we have been listening to lots of wonderful talk and lectures during these days. Valentina and many more have talked about the importance of copper in human cells. And that's the reason why we started thinking, well, copper is actually very important for cells. We have around 100 milligrams of copper each of us, and it takes part of different processes in our body. It's present, for instance, in the copper zinc superoxide dismutases, but in many other enzymes on this metal as a in their catalytic site. So copper is very important to the point that it's actually transported within the cell in a very balanced way. There are different copper transporters. Here you guys can see the CTR1, but there are many more. So the level of coppers are very highly regulated in our cells. And the reason is that, as you guys can imagine, if it is so important for our body, it's needed to be uptaken and to be used by our cells. But at the same time, excesses of copper can become lethal, and they can become lethal for many reasons. For instance, copper can easily access to the copper 1 oxidation state in oxygenated tissues, which are basically what our cells are. And for that reason, it can create reactive oxygen species, which can degrade some biomolecules, but also biomembranes, and induce apoptosis. So this last process can be used as a leverage of cancer. And here where our story begins, because we started asking if this compound, which was not a G-quadruplex stabilizer, could actually produce ROS. And if so, if this compound was cytotoxic to the cells, and again, if so, if ROS were involved. So we had these questions in our minds, and we could answer to them thanks to the work of Luisa Danna, our postdoc, and our PhD student, Daniela Ganci, who I really want to acknowledge for the hard work, and in collaboration with Professor Luparello from the University of Palermo. So the very first thing that we started doing was following the UVB spectrum of the copper complex over time, both in water and in buffer solutions. We immediately noticed that regardless of the conditions that we were using, we were always experiencing a loss in absorbance for this compound over 24 hours. We were talking about a 46% circa of loss, which was really interesting for us. And we also noticed that if we were to use some reducing agent, even biologically relevant one, like glutathione, we were always achieving the same extent of reduction of the absorbance of the copper compound, but with different rates. So the first thing that came to our mind is that, okay, this happens also with reducing agents. So maybe it's really a reduction of the copper center, but we had to prove it somehow. So for proving it, we decided to use a copper 1 chelator. So we added a copper 1 chelator over after 24 hours. For instance, we use the batocuprine disulfonate, which forms 2-to-1 complexes with copper 1. And it's very interesting because it has a very specific, peculiar band at 490 nanometers, which can immediately be used to detect the presence of such a compound. So upon 24 hours, we had the BCS, and we immediately noticed that in both the spectrum, either in the presence of ascorbic acid, but also without it, we could see this band. So copper-1 was formed, and the very next question was, well, can we use this to oxidize something? Can really ROS be produced? We decided to follow it by checking the oxidation of the reduced form of dichlorofluorescein, a very nice probe that once oxidized starts to fluorescence in the green. And with great surprise, we noticed that our compound could oxidize the dichlorofluorescein to the same extent of a 30% concentrated hydrogen peroxide solution. To be fair, our compound was even better because it could achieve the same extent in a 1-to-1 ratio rather than 1-to-5 as we used for the positive control. So, well, in a cell-free environment, we could produce ROS. What would it happen if we were to move to cells? Of course, we had to choose which kind of cells to use. And in this case, we decided to go for the hepatocarcinoma, HepG2. And the reason is that we needed to use a model which we could study quite easily. And HepG2 is a great model for this perspective because the ROS are produced only in mitochondria. So we had to follow to track just an organelle within the cell. So using this system, we immediately noticed that the copper compound was really cytotoxic for these cells, to the point that it was even threefold better than the cisplatin. We were talking about nanomolar cytotoxicity of the compound. Besides, if we were looking at the concentration, the cytotoxicity of the non-reductive active complex, basically the zinc one, well, you guys can immediately see that the zinc one is doing nothing. So probably the cytotoxicity of the compound is strictly related to the presence of the metal. Besides, and this is something that I really like to highlight, if you compare the effect of the metal alone or the ligand alone, you can immediately see that these do not match up. Basically, if you try to add these two effects, you don't get to the same point, to the same cytotoxicity that you get with the complex. This basically means that our compound has its own cytotoxicity, and again, that a copper complex, or better to say, a metal complex, can give some results, some cytotoxic effects to cells that a ligand alone cannot provide. So with this in mind, we started thinking of which mechanism was involved in this process. So we started analyzing the externalization of the phosphatidylserine by using the FITC labeled annexin 5. And we noticed that upon treatment, the amounts of cells that were undergoing either an early apoptotic or a necrotic process was basically the same. But what was really increasing was the amounts of cells that were undergoing apoptosis. So apoptosis was actually the way the cells were dying, and this was involving the activation of caspase 3 and caspase 5. And what was really interesting was also that we noticed the cleavage of the gasdermin family protein, which is very interesting because once these are cleaved, well, this means that there might have been an impairment of the mitochondrial functionality. So let's move to mitochondria then. When we started looking at the mitochondria, we noticed that the presence of a compound was inducing a dissipation of the mitochondrial membrane potential, which basically means that mitochondria were really affected by a compound. And it was really interesting because this affection, this dissipation of the mitochondrial potential was actually to the same extent as the golden standard that usually is used as a positive control, the valinomycin. So mitochondria were really targeted by our compound. And therefore the question was, were ROS involved in this process? The answer is actually yes. We used again the dichlorofluorescein, and we noticed that there was a kind of a threefold increase of ROS production upon treatment with our compound. So I hope I made the message clear, meaning that this compound complex could actually produce ROS either within and outside of the cells. And there are many questions that are needed to be answered yet. For instance, which ROS species are involved, or what's the importance of that NN bridge that we have over there. But still, there's one more question that I guess we should answer. That is, can we actually have something that targets the G-quadruplexes so it's so directed towards a cancer cell and at the same time produces ROS. So this is a question which is really not opened up yet. Luisa will deliver you the answer in a couple of minutes. But with this, I'm done for today. I just want to thank all the group, which you guys can see here in the pictures in both the summer version and in the winter version, yet still at the sea. Lack of living close by the sea. And I really want to thank you all for your attention. Thank you.
Thank you, Riccardo. We have just time for one question.
Oh, just an observation. You synthesize this complexity to target G4 quadruplexes, but at the end they don't target G4 quadruplexes. I understood correctly?
So they do target G quadruplexes, they do bind G quadruplexes, but they do not induce stabilization of the G quadruplexes, which is what we really want to have an anti-cancer effect. Sorry.
Thank you. Did you try to investigate also the activity against normal cells?
Okay, thanks a lot for your question. It's actually a very good one. At this stage, we didn't. We didn't because we decided not to push too much forward this, let's say, this family of compound. And the reason is that we know that the activity of this compound is cell-related. We know that upon testing other cancer cells, we saw that there was a different activity. At the same time, we want to achieve a targeted activity towards cancer cells by hitting first the G quadruplexes and then producing ROS. So we know that this is just a prototype that doesn't get to the cancer cells, so we didn't think that it was a good point to, let's say, investigate right now.
Thank you. Thank you again.
Thanks a lot.
The next speaker is Cristina Tubaro from Padova. She presents gold complexes with an heterocyclic carbene ligands, the rule of chalcosen functionalized substituent. Please, Cristina.
So let me thank the organizing and the scientific committee for giving me the opportunity to talk today about gold and heterocyclic carbene complexes with chalcogen functionalized substituents. And as you know, in the last 2 or 3 decades, there is an increased interest in finding alternative to cisplatin, considering the side effects that this drug has. And gold, silver, and we have seen copper complexes, so group 11 metals, are a good alternative. And this because, for example, this compound, which is auranofin, is already an FDA-approved drug for anti-arthritics, and it has been tested also for as anti-cancer drug, but it presents low plasma stability due to the labile metal to ligand bond. So we can change ligands in order to stabilize the metal complexes, and a class of ligands that have been widely studied in this regard, they are gold and heterocyclic carbene complexes, since it is well known that the metal carbon bond is very stable, very strong. So also the complex can reach the target without any variation. So I reported here some of recent reviews on gold application as anti-cancer drugs, and in particular gold and heterocyclic carbene ligands complexes. Another main advantage of using carbenes is that they can be easily functionalized. For example, by varying the backbone substituents, the nitrogen substituents, and we can introduce also different functions like this one that can possess themselves a bioinorganic or target. In this presentation, I will use simpler gold NHC ligands, with the substitution here with thiol, thioether, sulfoxide, or selenoether compounds. That because we thought to couple the activity of the gold complex with the activity of these chalcogen groups, which are present in proteins, in enzymes, and for example, the sulfoxide group is present in several natural compounds and can exert antioxidant and antimicrobial properties. So we started in 2021 with the synthesis of the thioether functionalized gold complexes, like this one. They can be easily obtained by transmetallation reaction or by direct metallation in the presence of potassium carbonate in very good yields. They have been fully functional, fully characterized in solution and also in the solid state. They present the typical linear coordination of gold 1. These compounds can be even oxidized quantitatively with the bromide to obtain the gold 3 compounds. And this is the crystal structure. And what is interesting in this case is that when we have the R1 substituent as an alkyl group, we have the interaction of the sulfur atom with a weak interaction of the sulfur atom with the gold center, and we have evidence this interaction by NMR spectroscopy. We have tested, unfortunately, these compounds only with one cancer cell lines, the breast cancer cell, and as you can see, the gold 1 and the gold 3 present practically the same IC50 values of cisplatin under the same conditions, and the gold 3 compounds and gold 1, the corresponding gold 1, have the same activity. That because the gold complexes can be reduced in the presence, for example, of glutathione, which is present in a physiological condition, and we have demonstrated this also by NMR. We moved to another class of chalcogen functionalized groups, which are the sulfoxide groups. And as I mentioned before, sulfoxide moieties are present in several natural compounds. Even in this case, the synthesis is very straightforward. We adopted a transmetallation reaction. We obtained the complexes, and we tested them towards a larger variety of cancer cell lines. I will not enter into the details of this table. What I would like to underline is that these compounds here in yellow, which are the precursor of the carbenes, are inactive. The gold 1 and the silver 1 complexes are active in the order of micromolar, like IC50 values. The values are higher than cisplatin or auranofin, but they present a moderate to good cytotoxic activity. They are active also in cisplatin or oxalylplatin or multi-drug resistant cancer cell lines with resistant factors, in some cases, significantly lower than cisplatin, like in this case here towards these cancer cells. So we can see that all the values are around 1. So they present the same activity in the, let's say, normal cells and in the resistant ones. We have also studied 3D models that mimics, let's say, the mass of the tumor, and the complex with the benzyl group and the phenyl group as substituent to the sulfoxide present the best activity. The gold ones complexes are more active than the silver ones, and in this case, the activity of the gold complex is comparable to cisplatin, and in these different cancer cells, it has an activity more or less 7 times higher than cisplatin. We have also investigated the mechanism of action, and the gold 1 triggers TRXR activity. So we have it inhibits the TRXR activity in the range of the nanomolar concentration. And the difference between the gold and the silver complex is that silver affects also the GR activity, while gold complexes do not affect the GR activity. And the inhibition of TRXR causes obviously the formation of Ross species that ultimately give apoptosis of the cell. So this is the mechanism of action of these compounds that we have investigated. And in detail, the other classes of compounds, we have not yet investigated all the biological activity, but I will present you the synthesis of these compounds. For example, we moved to thiol functionalized arms or substituents of the nitrogen atoms. Even in this case, the synthesis is quite straightforward until this step. So until the sulfur atom is protected in the form of the thioacetate. The last step, which is the deprotection of the thiol function, is a little bit tricky. You need to adopt a strictly inert condition of absence of oxygen. And for this reason, the yields are quite low. But once you isolate these compounds, it is really stable even in the air. You can fully characterize it, and the formation of this type of compound is can be easily seen by the proton NMR by the presence of this quartet, which is the last methylene group close to the thiol function. They are so stable, even in the air, that they can be also crystallized, as in this example here. We are currently studying the activity of these compounds, both the thiol and the thioacetate functionalized gold complexes, and but I do not have now the results. I have some preliminary results with the last class of compounds that we have studied, which are the selenium ether. In this case, they can be obtained by direct metallation in the presence of potassium carbonate. The seleno function is as a phenyl group as a substituent. You can obtain the neutral complexes and also the cationic ones with in the form of biscarbene compounds. And they crystallize, they are very stable, and they can be used. They are stable also in solutions mimicking the physiological ones. And we have some preliminary results towards only 2 cancer cells. Again, I would like to underline that the precursors of the carbene, which are the imidazolium salts, are not active. The gold one complexes are active, in particular the 2E, which is the one with the R group as benzyl group, and here we have the phenyl group as a very high activity, higher than the reference drug, which is cisplatin. And in this particular complex, we can see that the role of the selenium center, because if you compare the activity of 2E with that of 2B, which is this compound without the selenium, we can see that it is the IC50 values in this case are higher than the complex with the selenium. And we are now trying to understand the role of this functional group. So I would like to conclude the gold one complexes can be easily obtained. We can insert the different functions in the lateral groups of the nitrogen substituents. They present moderate or good anti-cancer activity, in some cases comparable or higher than cisplatin. We have investigated the mechanism only with the sulfoxide functionalized NHE, but we are currently studying also the other compounds. And I hope in the future to have all the data and to see which functional group is better, in order to find a structure-activity relationship. At the end, I would like to thank all the contributors of this work, in particular Irene and Eleonora, and Professor Valentina Gandino of the Department of Pharmaceutical Science in Padova for the biological tests, and the CNR in Strasbourg as well. All the group of organometallic chemistry in Padova, and all of you for your kind attention.
Thank you, Christina. You have time for a couple of questions from the audience. Okay, I have one.
Yes.
I'm wondering if, in the case of the selenium derivatives, did you associate a special function to the presence of selenium with respect to sulfur? And in case, do you have some information with the selenium-77 NMR spectroscopy or not?
Okay, we have run the selenium-77 NMR spectroscopy. We don't have any indication of, at the moment, to justify the difference between sulfur and selenium. We know that selenium compounds are used as antioxidant, for example, so for this reason we decided to insert this function, but we know that that function is stable, so we are now trying to finalize this work, but then moving to introduce a selenium function with a bond that can be broken in other physiological conditions, so we can have the gold from one side and the selenium function from the other. But at the moment, we are not able to justify the difference between sulfur and selenium.
Riccardo.
Ciao Cristina, lovely work, congratulations. I was really impressed by the thiol-based compounds. And I know you love, and I know the reason why you love. So I've seen that you have been using different lengths in this chain. Did you by any chance experience any intramolecular coordination with the thiol?
Yes. Okay, to be honest, we were synthesizing the thiol functionalized compounds for other purposes, which were catalytic ones. And so we needed the long chain, but then the long chain is also necessary in this case, because if we have shorter chains, like for example 2, 3, or 4, the yields are much lower than 30% because we observe the cyclization between the carbene and the sulfur. So we need a long chain to stabilize the thiol function, and otherwise, yes, we have this side reaction. So in solution or in the solid state, we didn't observe interaction of the thiol group with gold, probably because we choose this long chain. We hope to have an interaction between this thiol group with biomolecules when we finalize to test them, but we need the long chain.
Let me thank again Cristina. It's my personal pleasure to introduce the third speaker of this session. Her name is Daniela Pappalardo from the University of Sanya, and the title of her presentation is Double Responsive PCL-PEG PCL-based nanoparticle, a new life to an old drug delivery system.
Good morning, and thank you, Mina, for the nice presentation. I'm going to present a result regarding novel tri-block copolymer based on polycaprolactone, polyethylene glycol, and polycaprolactone, used as a drug delivery system, as the dual responsive system. In this audience, I'm sure you know that drug delivery systems are supramolecular assembly that are used to incorporate a drug to treat a disease. They are, our focus was mainly on polymeric nanoparticle for intravenous injection. It is well known what are the conventional drug administration failure disadvantages, while which can be the advantages of the using of DDS, especially the possibility to avoid drug degradation, to increase the drug bioavailability, and to avoid unfavorable side effect. What is the biological rationale behind the use of drug delivery system? This is mainly focused on the so-called enhanced permeability and retention effect, which is based on the size of the polymeric nanoparticle, which should be around 100 nanometer. If it is so, it happens that the polymeric drug is preferentially entrapped into the tumor tissue, since the angiogenic vessel behind the tumor are usually more fenestrated to they allow the accumulation of the polymeric nanoparticles into the tumor tissue, avoiding the healthy tissue where the vessels are very tight. So with this idea, we were looking at the literature. It is also very known that unfortunately the EPR is highly debated in the literature, since in most of the case the drug is found in the urine, is excreted by renal route. So a new class of stimuli-responsive DDS have been developed that could respond to external stimulus like temperature or light or magnetic fields, or also internal stimulus, that means the one that are found inside the cells, for instance pH or enzyme or reduction environment. We were interested in the use of light, and in particular in the use of near-infrared light. Why? Respect to the visible and UV light, the near spectrum is recognized as are safer, and moreover it has a deeper penetration into the tissue. What about the kind of polymeric material? We look at the literature. If you are interested, you can also read one review that we recently published on the subject. And perusal of the literature showed that while there are a lot of light responsive group that can be used, the use of the biocompatible polymer is very can be counted on very few examples. Our idea was to use this polyethylene glycol block polyepsilon caprolactone copolymer, since this has been used for ages in the literature as system for deliver a drug in a safe way. Why both block are biocompatible, non-toxic. In particular, PCL is hydrophobic. It can degrade in the body, giving rise to a fragment that can enter in the Krebs cycle. PEG is hydrophilic. Is not toxic, and I largely use it for this kind of purpose. Of course, this kind of amphiphilic block copolymer, when are in water, they could self-assembling micelles, where there is a hydrophobic core constituted by the PCL, in which an hydrophobic drug can be entrapped, and PEG constituted the corona of the micelles. Well, how to make this kind of system a responsive system? So our first aim was to design a kind of polymer, a tri-block copolymer, bearing the PEG as a central block, then the two PCL block, ended with a coumarin. A coumarin moiety is known from the literature that can, in particular the ester bond, can be broken by UV or near-infrared light irradiation, giving rise to the breaking of the bond, formation of a carboxylic fragment and alcohol coumarin. And then this system can be used to unbalance the ratio between the hydrophilic and hydrophobic blocks, so provoke the opening of the micelles. So we have synthesized as actually this kind of 3-block copolymer. I will not show for brevity the synthesis. And we have proved that this kind of copolymer could give rise to self-assembly in water phase, forming micelles. We used Nile red as a probe of a hydrophobic molecule, of a model of hydrophobic drugs, and then we tested the photolysis reaction under UV or near infrared light irradiation. And to be short, what we saw was that under in the dark, the kind of micelles were stable for 6 hours. We monitored the fluorescence emission after near infrared light irradiation, and we saw that there is a drop of the Nile red fluorescence after irradiation due to the fact that it is not soluble anymore in water phase, while it is soluble in the hydrophobic core on the micelles. That means that after irradiation there is the breaking of the expected there is the detachment of the coumarin, the imbalance of the hydrophilic hydrophobic ratio in the micelles, so the release of the Nile red. However, also the literature show that sometimes the use of one stimulus is not enough to guarantee an efficient release. And so the further aim was to improve this kind of micelles, introducing another responsive group. In particular, we focused our attention on sulfur-sulfur bond, which are well known to be redox responsive, in particular in the presence of glutathione. Is known that in the extracellular environment the concentration is low, is around 10 micromolar, while into the intracellular environment the concentration is around 10 millimolar, is higher, and the sulfur-sulfur bond can be reduced. So how to achieve this kind of macromolecular structure? We started from pegdiol, 2000 Dalton, then we used succinic anhydride to form carboxylic acid end groups, and then we made esterification by introducing this diol bearing the sulfur-sulfur bond, Serlich esterification to form the desired molecular chain. This prepolymer was used for the ring opening polymerization of epsilon caprolactone in toluene solution. So we achieved also the terminal PCl block, and then again Esterlich esterification with succinic anhydride to get again the carboxylic acid, and at the end esterification with the coumarin alcohol that was prepared according to a literature procedure starting from the methyl coumarin to get at the end desired tri-block copolymer with double functionality. Of course, we have characterization of all the steps of the reaction. For brevity, I show quickly the NMR result of the final copolymer. Diagnostic signals is the CA2 bounded to the coumarin, as well as the dose spectrum showed a nice one line of all the signal of the copolymer, indicating that we have not a mixture of different species, but just the copolymer that we have designed. Now, how to prove that the system works as we intended? We got again a nice nanoparticle, flower-like shape, dimension in the size that we desired, and then we tested the irradiation by the light irradiation. We saw again, as showed before, a drop of the Nile red fluorescence after irradiation UV and also at 800 nanometers, so in the near infrared range. What about GSH behavior? The nanoparticles are stable in 10 micromolar concentration of GSH. That is the one that is found into the extracellular environment. After increasing the concentration to 10 millimolar, we observe a gradually but also quite fast decrease of this fluorescence. But then, what happens if we used both the stimulus together? We compared the result of the irradiation, in this time UV irradiation, in presence of 10 millimolar concentration of GSH with those obtained after irradiation, UV irradiation alone, and in the presence of GSH addition alone. And what we observed that there is a faster release of the Nile red that is a good indication of a synergistic effect. We have also carried out in vitro study on human dermal fibroblasts. Quickly cell viability was good, and also fluorescence microscopy disclosed that the internalization of Nile red nanoparticle, Nile red loaded nanoparticle was higher after 24 hours respect to Nile red alone. In conclusion, we can claim that this kind of nanoparticle could be useful for the release of hydrophobic drug with the spatio-temporal control. And last, let me thank people who worked on this project, in particular Nancy Ferrentino. She did a PhD on this subject. Collaboration, in particular Professor Anna Finne-Wistrad from Royal Institute of Technology of Stockholm. Funding, and of course all of you and the organizing committee for this opportunity.
Question for Daniela. Signorina.
You synthesize 3 block copolymers. The size of the blocks is the same, or there are different?
No, we try to keep roughly 50-50 ratio between the PEG and epsilon caprolactam in order to achieve better stability of our nanoparticle. This is known from the literature, so we use this kind of ratio.
Okay, why you choose 3 block copolymer?
Because
not
die block.
different number of
Yeah,
blocks?
this is good question. It's also known from the literature that tri-block are more stable respect to di-block, since they can give rise to this kind of flower-like structure, where you have the loop of the PEG outside, and then you have the hydrophobic block together. And also we notice, as I haven't had time to show, that there is an increased stability due to the coumarin, probably due to the pi-pi's interaction. This makes even stronger the stability of the nanoparticle.
Thanks.
Thank you.
Thank you, Daniela. It's time for the next speaker, Luisa Danna from the University of Palermo. The title is quite long, Riccardo, so... okay, so it's an habit of the group. And unlocking G4 DNA affinity through aromatic side chain, a comparative study of nickel, copper, and zinc-2 Salnafen derivatives.
Okay, so morning everyone. Today I'll tell you something more about the topic Riccardo Bonsignore has already introduced you before, and particularly I'll tell you something about the importance of the functionalization of Salnafen derivatives in the interaction with G4. So just to set the context, G-quadruplex is one of the secondary structure of DNA. It is formed in a guanine-rich sequence where guanines can interact with each other through Hughes-Stinn base pair, forming a tetrad. At the center of this tetrad, we have a central channel where monovalent ions such as potassium are located, and these ions can stabilize the conformation. Depending on the orientation of the strands, we can define the secondary structures of, in parallel, anti-parallel, or hybrid. And also important are the loops and the groups that are important for the interaction with the small molecules and that can help us to define the whole conformation of G-force. So it's interesting to note how G-quadruplex are present in many genomes. We can find them in viruses, in bacteria, and also in human genomes. In particularly, we can find them in telomeres, in gene promoters, and in general in regions related to cancer development. And when a G4 forms in these regions, we can have the alteration in processes related to cell proliferation, such as transcription or transduction. So in this field, the main goal is to achieve a selective targeting. So we want to find small molecules that can interact selectively with G-quadruplex, that can interact through pi-pi staking or electrostatic interaction with the tetrads, the loops, and the grooves, in order to stabilize the conformation and to alter the expression of the protein related to the pathological condition. Our research group is interested, among other, as already Riccardo told you, in sulfate metal complexes. The main features of these compounds are the planar geometry given by the coordination of metals such as platinum, palladium, copper, nickel, iron, and zinc, the extended aromatic area, and the possibility to play with the functionalization to modify the properties of the compound, and so the interaction with the G4. Here I report some of the compounds that we already studied in the last few years. The problem in this field is to find the best compromise between all the properties, between all the features. And so, for example, the selectivity towards the different G4, the interaction strength, and the solubility. So that's where our question comes in. So Riccardo before told you how can we optimize the anti-cancer properties and the binding properties with DNA. So we tried to answer this question by synthesizing these three new derivatives bearing an N-methylimidazolium side chain. And we compared the effect on G-quadruplex and on cells with the previous one that we already studied with the triethylammonium side chain. Here I report the synthesis. We started by isolating the N-methylimidazolium aldehyde, and then with a one-pot reaction, we obtained the compounds with the high yields. So at first, when we synthesize new compound, we perform a FRET assay. With this experiment, we evaluate the stabilization profile of our compound by the evaluation of melting temperature of the selected G4. And if we look at the graph A, these compounds show a certain degree of selectivity because they stabilize very good CK1 and HTLO. If we look at the results from the point of view of the compound, we can see that zinc derivative is the weakest one, while the best results come from copper compounds that can stabilize better than the other HCl and KIT1. So we performed also UV-Vis experiments. As you can see from this graph, we can say that our compounds effectively interact with HTLO. Here I report just the result with HTLO for a question of time, but we performed also with the KIT1. And we can say that thanks to the hypochromic effect of the bands. But if we look at the binding constant of the different compounds, we can see that derivatives 2, so the one with the N-methylmidazoline side chain, binds to the 2 DNA fold higher of magnitude than the derivatives with the 3-ethylammonium side chain. So how we can explain this difference in strength and in stabilization? To answer to this question, we performed the molecular dynamics simulation, and what we find out is that the presence of an aromatic side chain can get an additional interaction with the loop nucleotide, and it is something that miss in the compound with the 3-ethylammonium chain. This is probably due to the bulky 3-ethylammonium chains that prevent the compounds from approaching closely enough to interact effectively with the G4. Additionally, from the molecular dynamics simulation, we saw that probably there could be a coordination of the central metal with the oxygen of the guanines of the tetrad. So this could explain the better interaction strength with the G quadruplex. So looking at the biological results, we performed antiproliferative assay with 4 different cancer cells. Once again, the best results come from copper compound. As you can see, is the best one in terms of IC50. And weak results come from zinc and nickel derivatives. So, as Riccardo told you before, copper can induce ROS production in cells. That's why we performed a ROS production assay in MCF7 cells. And what we find out is that, once again, copper can induce ROS production in this kind of cells. And at the highest concentration test, it can outperform the results of the ABAP benchmark. This is a result that we cannot see with the other 2 derivatives. So what we can say at the end is that when we rationalize new sulfate metal complexes, of course we have to take into account the lateral functionalization, the metal center, and what we can say is that copper shift-based complexes could be considered as a multi-target anti-cancer agent, combining both DNA interaction, and specifically G4 interaction, and redox-based cytotoxicity. I finished with the... Thank you for the attention, and thank you to my group from Palermo for everything.
Thank you. You were very fast. Question for Anna? No? I have just a curiosity. I'm not an expert of the field, so I'm sorry if my question is not very smart, but it seems that planar elements are always important. It's easy to change this new group that you introduced with another heterocycle substituent, or it's quite difficult to introduce another, for example, pyridinium
No, yeah, we tried to add other functionalization with aromatic rings. The results are promising. We introduced a pyridine, if I remember correctly, and the results are quite good. But also in that case, there is always something that misses between selectivity or interaction strength. So this is something that we need to understand. That, yeah.
Maybe I lose this information. The intercalation increases the melting point of G quadruplexes or decreases? Intercalation of the complexes.
It depends. So we cannot know if the
because you relate intercalation
but it's not
melting.
Yeah, it's not dependent. So the stabilization can depend also, for example, from the interaction with the loops. So it's not only the intercalation that give a stabilization.
So there is not a direct relation between melting point and intercalation.
We evaluate the melting point, but we cannot know. We can know where our compounds interact through, for example, molecular dynamic simulation. But with the FRET assay, it's difficult to know where the compounds interact with them.
Okay,
so it's not correlated.
The melting point is not indicative of a better Eiger intercalation ability? Or
No.
Okay, thanks.
Just a curiosity, do you have idea how did do this complex enter in that cell?
No, this is something that we need to study. These biological assays are preliminary, but of course we want to know how the compounds enter in cells, because this is a good point, because for example with the compound that Riccardo showed with you before, we saw better cells result and better antiproliferative results with the HepG2 cells. The complex is quite the same, the mechanism is quite the same, but probably the uptake is different. So probably the answer is the different uptake.
Compliments for the presentation. It was very clear. Just a curiosity about the molecular dynamic simulation. How much long the simulation time in this case?
Is 1 microsecond.
1 microsecond. With replica?
Yeah, 2 replicas.
Okay. Thanks.
Thanks again.
Absolutely.
The next speaker is Mohit Chawla. Okay, the next speaker is Mohit Chawla from KAUST, Saudi Arabia, and the title of his presentation is Accurate Classification and Detection of Atomic Interaction at Biopolymer Ligand Interfaces.
Hi, everyone. Thank you very much for the kind introduction. My name is Mohit. I must tell you that, initially this presentation was scheduled for Professor Romina Oliva from University of Parthenope, and unfortunately she couldn't join, so I'm just giving this talk on her behalf. So the title or the work that I'm going to present today is about the accurate classification and detection of atomic interactions at the biopolymer ligand interfaces. So, okay, before we, dive into the real, tool that we have developed, like I'll just try to introduce you to the various terms, okay, that you will be seeing in the next couple of slides. So when I say like the ligand interacting with biomolecules, okay, so the ligand that we are using, they can either be organic or inorganic, and they can both be the functional and the non-functional ligands, right? And when we talk about the biopolymers that we took into account, they are DNA, RNA, and also proteins. And of course, like we can have as complex, targets as like the ribosomes, in which we have the RNA complex with the proteins interacting with, various organic and inorganic ligands. Okay, so this is one of the example, like where you could actually, where you could see like, how, the binding site of a protein is captured. Like, okay, if there is a ligand that is binding to, a protein, and most of the residues that forms the binding pocket, they are highlighted here. So there is another example wherein we have a ligand which is as small as a guanine that binds to a guanine riboswitch, which with the key residues lined up in the binding pocket highlighted here. Okay, so the identification definitely and characterizing the ligand binding site is very important, specifically to study the modulation of protein RNA functions, along with the information driven drug designing applications. Okay, so as we have heard, like in the recent talks, the ligand, when they recognize the biomolecules, the main driving force is the molecular recognition, right? So the molecular recognition, it occurs at the atomic level. So in this particular work, we have developed a code that accurately classifies the unique, the non-covalent interactions at the ligand and the biomolecular interfaces. Okay, so these are the list of all the interactions that we have characterized and identified using the tools that I'm just going to explain. Now, if you look at all these interactions that range from classical H bond to the weak bonds, weak hydrogen bonds, the water-mediated salt bridge, and so on, most of them are clearly weaker than the classical hydrogen bonds and pi-pi stacking. And of course, they are very much relevant for fine-tuning, the binding affinity. And, like this can, of course, be comprehensively used, to train the machine learning algorithms in case, the computational biologists are interested. Okay, so now, of course, like there are plenty of tools that are available till date in literature that describes some of the interactions, but they lack the comprehensive classification. So the underlying the interactions that I have mentioned here are the ones that are quite novel, that we have incorporated in order to get it detected when the ligand is present at the interface between the biomolecular phases. So apart from these 15 unique interaction types, okay, let's suppose like we have the binding pocket, and we cannot classify the interaction between a given ligand atom and the biomolecular surface with any of these interactions. We simply mark it as a proximal interaction because we do not know the real definition, like how exactly it is interacting. Okay, and also like for many of the modeling exercises, like okay, the interactions that that fall below the sum of the respective van der Waals radii for two specific atoms, we mark them as clashes. And of course, they can be very much useful when people are modeling, the ligand at the interfaces, and specifically when they are performing the docking experiments and also the molecular dynamic simulations. Now, this raises a question like, okay, the classification that I have just explained is, of course, based on the literature studies, including our own studies. Okay, so like recently we have characterized like some of the novel interactions, specifically in the structures of nucleic acids. They are, the anion pi and the lone pair pi interactions. Specifically, we talk about the, lone pair pi interactions when we have the oxygen from the ribose sugar that stacks over to, the nucleobases, the A, U, G, C in RNA, and also the aromatic amino acids in the protein structures. And then we have also characterized the anion pi interaction specifically, like for, specifically in the cases where we have the phosphates, they are, stacked over to the nucleobases. And we kind of, simply took the classification scheme, like from wherever it was available from literature, along with our own studies that we have carried out. Okay. Now, to present the real analysis and the classification tool, okay, we present a tool which we name it as NAPOLI. NAPOLI simply stands for the Nucleic Acid Protein Ligand Interaction Analysis. as a fun coincidence, like I'm just presenting this tool while I'm in a beautiful city, Napoli, right? So, so if you really look from the perspective that how we have developed this tool, it kind of accurately, sorry. It kind of accurately carry out the comparison of the interfaces specifically related to the atomic level interactions, right? And we deal with the ligand proteins along with the ligand RNA DNA complexes. Okay, so I'll just quickly walk you through the tutorial, like how you can really utilize this tool for your research work, since I saw like a couple of presentations like that are dealing with the metallo drugs interacting with the DNA, with the proteins, right? So of course, like when you're performing molecular dynamic simulations or you're analyzing the PDB structures, you might be interested like how exactly the interactions are occurring at the atomic level. Okay, so in that case, maybe our tool might be of some relevance, right? Okay, so I'll quickly walk you through this tool, like how you can simply use it. We simply have to input a PDB code. Okay, our tool simply accepts the PDB, any structure having the PDB or MMSIF format. Of course, now we have implemented a new a strategy in which like it also accepts the extended PDB formats, because now the PDB formats are getting obsolete, right? So we have the extended PDB formats and the CIF file formats that our tool can simply accept. You simply enter the 4-letter code, okay, or the extended PDB code here, okay, or you can simply upload the file. If you have your file from the molecular dynamic simulation trajectory, any snapshot from docking, right? So you can simply upload the file and simply click on this, the identify nucleic acid ligand interaction pairs. So what it simply does is like it will simply scan the PDB file from the backend in order to identify the possible ligands that we have in the PDB file or the CIF file that we are studying. Okay, so you simply click on this button, identify, and once it identifies all the possible ligands, it will give the list of ligands that are present in your PDB structure with the corresponding chain and the residue number and the chains of the biomolecular species it is kind of interacting with. So in this particular case, like there are the 2 chains in which that are specifically interacting with this particular 6UQ, which is a ligand. Of course, like we have set up the default parameters in order to detect these interactions. However, if you want to play with the different cutoff values, you can always tune in and change the parameters. Okay, so as if you're a non-expert, like let's say like it's better not to change this because all these values are set by default considering the extensive literature and our own analysis from the theoretical studies. Okay, so now I'll just show you a simple example of an organic ligand, which is an avilamycin. It's an antibiotic that is bound to a protein and the 23S ribosomal RNA for 50S ribosomal subunit. So on the right, you can see a 3D visualization in which we have the ligand that is interacting with the gray color is the nucleic acid, the RNA, and this orange color is the protein that it is interacting with, and all the interactions are color coded. Okay, and on the left side you can see a wheel chart in which on the center you can see the ligand and how exactly it is interacting with the residues that it is surrounded with, which are the kind of interactions. So they are all color coded according to the different interaction types. So apart from this wheel chart, like we have 2 more interactive graphs, which is a distribution, the donor distribution chart, that simply displays that how frequent or predominant some interactions are as compared to the other ones. So you can just relatively get an idea like which interaction is more common than the other in the structure that you are studying. And then like we have the corresponding heat map that displays the number of contacts between the ligand atoms and the biomolecule your thing is interacting with. Now, all these charts are kind of very interactive, and we also give, a detailed, a table in which you can actually see that, the classification of the residues along with the ligand, whatever is interacting, along with the type of interaction it is making. If you really want to dig deep into that, what you can simply do is you can just click on any of the rows and simply get more information related to which exact atoms are interacting with, the ligand and the biomolecular thing that you are working with. Okay. Apart from the interaction analysis, we also deliver the statistics related to the accessibility, the accessible surface area along with the buried surface area. And on the right, you can simply see, the structure of ligand in which all the atoms are coded, the color coded with respect to, how buried or solvent exposed your ligand is. So you can see on the top, like this particular part, just by looking at this visualization, you can see like this particular part is deeply buried. So this is the area which is kind of interacting. And this is the area which is kind of, more solvent exposed. And apart from that, like we give, the buried surface area, and the accessible surface area statistics for, the residues that are forming the binding pocket. Now, this is another example that you guys might be more interested in, since this conference is related to, bio-inorganic chemistry. So like I show you one example of a ligand, the oxaliplatin that is interacting with the DNA dodecamer, okay, and corresponding like how this platinum is kind of coordinated to the ligand along with the N7 atoms of the guanine, which is present in the 6th and 7th residue, and the corresponding, the wheel chart. So that particularly and relevantly discern that, okay, there can be the metal mediated context to stabilize the structures. Now, we have discussed, the details, but just looking at some technical details, of course, like there are, many ligands that are present in the PDB. Like if you look at simply the PDB database, we have over 46,000 ligands that are deposited until today, right? And these numbers keep on increasing, right? So, and if you look at the real PubChem source, like there are more than 121 million ligands that are there, right? So of course, like it becomes quite challenging because, the chemistry of proteins and nucleic acids for the standard amino acid and nucleobase is well known, right? But for the ligands, like they are quite diverse, considering that all these ligands are unique, right? And we can have, a different, the features corresponding to different ligands we are studying in. So we need to pre-process all the ligands in order to find out all the geometrical, aspects corresponding to it, and in order to find the ligand features. Okay, so this is how a ligand will look like when you see the PDB, right? And first of all, like we need to like add the hydrogen atoms, right? And of course, then we need to find out all the geometrical parameters so that we can calculate all the interaction types that we are incorporating in our tool, right? And for the ligands that are present in CCD, it's pretty easy to model. Like we have just created a pipeline in which you simply add the hydrogen, and because this information is already there in the CCD, the Cambridge structural database. Okay, and then we have for the non-CCD ligands, suppose like you're modeling a ligand, right? And this ligand is not present in CCD. Of course, like we use different tools like the RDKit, OpenBabel, and Chimera in order to study these things. Okay, so to conclude, like we provide accurate detection of the atomic interactions between the biopolymer ligand interfaces, and which captures like 15 unique kind of features, ranging from hydrogen bonds to pi to metal mediated contacts. Our tool is able to handle the complex, ligand macromolecular assemblies, okay, ranging from, PDB to the large ribosomal subunits as well. And it offers, a comprehensive ligand-centric outputs in terms of, the detailed visualization charts that you can, it is quite intuitive when you look at chart, like everything is clear. And then of course it is open source and extensible, which simply means that you can really use all the features for, various computational analysis and also for the machine learning applications. So with this, I would like to thank first Professor Romina Oliva. She has been, leading this project. And of course, the discussions with her at every point were very beneficial, since she's an expert in computational biology and chemistry, like developing tools. Like she has extensive experience in that. And then the support, and thoughtful discussions from Professor Luigi Coelho, who is my, boss, a manager in Saudi Arabia. And then Professor Abdul Razak Sheikh he's now visiting University of Parthenope, Naples, with Professor Romina Oliva. And then Andrea Petta and Utkarsh and Suresh, George Magdaleno, these all people were involved in, designing the front end and the back end support for this tool. With this, I would, if you guys would like to access this tool, of course, this is a QR code. You can just save this. And since we are now at the debugging stage, okay, your inputs will be more than welcome, in order to make this tool beneficial for the structural biology and the computational chemist society. Of course, if you have any questions, you can always, email Professor Romina Oliva or me, and we'll be happy to discuss further on that. I took a few more minutes, yeah, and thank you very much for your kind attention. Thank you.
Thank you for describing this important tool. Any question? If not, thanks again.
Okay.
The last speaker today is Francesca Forti from the University of Bologna. Francesca. The title of her presentation is a comprehensive investigation of highly reduced iron carbon carbonyl cluster, a pathway towards nitrogenase cofactor modeling. Please.
Hello, thank you for being here on the very last lot of the oral presentation. So I hope it will be a nice hand for you. So these are our latest research on this iron 6 carbide carbonyl cluster towards nitrogenase cofactor modeling. So very, very briefly, metal carbonyl clusters, or MCCs, are compounds composed by at least 2 metal atoms bonded together in an oxidation state, stabilized by a shell of CO ligands, which stabilize the metal core through the synergy of sigma donation and pi back donation. For the cluster that you will see here on this presentation, we have focused on homometallic carbide clusters. So you can see that inside the metal cage, the iron metal cage, there's one interstitial carbon atom coordinated to every metal atom in the cage. Here you can see the nitrogenase active site, which is called iron molybdenum cofactor. As you all know, nitrogenase enzymes are the only enzymes known in nature to successfully catalyze a fundamental step in the nitrogen fixation, which is required for every form of life, for life as we know it. What is interesting about this fragment of the enzyme is that the precise structure is very recent. It dates back just a few years ago, when they discovered that inside the iron sulfur moiety ensemble, there is one carbon atom bonded to the iron, to all the 6 iron that you can see there. So this generated the so-called carbide problem, which, as far as you know, is the near impossibility to incorporate a carbide atom inside an already preformed iron sulfur cage. So one way to tackle this problem is to reverse the strategy, so to synthesize and use a already preformed iron carbide cage and then try to functionalize the cage with S-based ligands without the breakage of the cage itself. So a lot of studies in this sense have been done, and also us in our lab with the compounds that we are familiar with, so metal carbonate clusters. So one way to do this is to use, as you see here, this metal core here, iron 6 carbide metal core, in this case surrounded by a shell of 15 ligands. And this is the cluster that we have used as our precursor. It's very reactive and also highly reduced because it has an overall charge of 4-. So this was the very first oxidation reaction synthetic path. So starting from our precursor, we try to investigate the functionalization of cage, and in this case, oxidation without fragmentation. So first of all, you can see that if you use harsh oxidants like methyl iodide here or strong acid, we cause the breakage of the cage. This is a very known iron 5 carbide cluster known in literature. The other one is a new compound, this one, but still with the breakage of the cage. So we are not interested in this type of cores, metal cores. While when we use milder oxidants, like this one listed here, we obtain the homologous, oxidized homologous of the precursor. So the same iron 6 carbide cage, but with an overall charge of 2-. And also you can see that between the two, we have a difference in one CO ligand. So the introduction from the 4- to the 2-, we have one addition of CO ligand. So that's where we want to place our CO substitution with other type of ligands. So we have tried to perform this oxidation with a trapping agent, so other ligands, for example, carbonates, PTA ligands, and in this case, we have successfully functionalized the cage without the breakage of the cage itself. So we were successful in this case, while when we use other ligands, for example, triphenyl phosphide, like here, more hindered, this is a new compound, but still cage breakage, iron 5 cage. So what we can conclude is that the cage retention in this case highly depends on the trapping agent used, on the nature of the trapping agent used. So this is what we were most interested in. So at this point, with Professor Funaioli, we decided to do some IRSEC, IR spectroelectrochemical studies on the oxidation mechanism of this, our precursor 4- to better understand the intermediates involved and the possible mechanism. So you can see here on the top, there's the oxidation of the 4- from here to here, to the 2-. And on the bottom is the potential backscan that in fact is the reduction from 2- to 4- again. So first thing to say, in these conditions, that is Otto cell argon atmosphere, the reaction, this oxidation reaction is perfectly reversible. Second thing to say, we can observe this unknown band, unknown at that time, a band around 19 centimeter at the power of -1, here and there, that is decreasing after the oxidation. So it's growing and then decreasing. Probably this is a trianionic species. We can hypothesize that is this species right here, trianionic species, and intermediate. Because if we look at the overall reaction of oxidation, it's a 2-1 electron strap process with the addition of a CO ligand, as I said before. And this can proceed either via ECE or EEC mechanism, those two, and both of them include, after the loss of the first electron, this trianionic species. That probably is the intermediate that we see. So Professor Bortoluzzi did DFT calculations for us in order to discern which was the mechanism, in this case involved, any calculating the intermediate relative stability. At the end, we conclude that this mechanism undergoes EEC mechanism, so electron-electron chemical process. So first we have the 2-1 electron loss, so the proper oxidation part, then we reach this intermediate, which is a 2-, and then to complete the shell of ligands and to reach the homologous iron 6 carbide 2-, we have to add 1 CO ligand. What we see is that probably this is the one that is accumulating in the cell. So we have been able to see it experimentally, because the bottleneck of the entire process, while these 2 electron loss are very, very fast, is the addition of the CO ligands, because it's not present inside the atmosphere of the cell, which is argon, but the CO can only come from decomposition of the main cluster, so decomposition to smaller cluster, iron 5 carbide, iron 4 carbide, etc. So that's probably why we can observe this intermediate. And also Again, as I said before, this last passage is the one that is interesting because in order to complete the shell here, we can place another ligand. In this case, finally, we have been able to use S-based ligands, organic ligands. So after a lot of work, we have been able to develop this relatively simple synthetic path to synthesize clusters of this type, iron 6 carbide, CO14, SR3-. And these were the first attempt and also the first successful functionalized as iron 6 carbide cage with organic sulfur. So this reaction can be considered quite robust. It works at least for the thiols and the disulfurs that I've listed here. And these are some of the XRD structure of the compounds that we have been able to crystallize. So after this, we tried to expand our reactivity, our little scope, using as-based compounds, as ligands, the cysteine, which is also the one that is bonded, the amino acid that is bonded to the nitrogenase enzymes. And we have been able to synthesize this cluster, which is a bit more difficult to crystallize, so we have never crystallized it so far. And we have characterized by IR, NMR, and you will see later VCD. So this is the DFT structure. The one that you observe here is the DFT structure that Andrea Pellegrini made for us. So since this was the first example that we have of ligand with a chiral center, and in order also to further characterize the compound, we decided to perform some VCD, vibrational circular dichroism experiments. And of course, unlike all the other blank tests, iron 5, iron 6, all the other carbides that we have, iron carbides that we have, we observed that the cluster with the cysteine has this very quite intense signal in the CO region of the stretching of the CO of the cluster. These are two opposite signals, both for the compounds with L-cysteine and also D-cysteine that we have tried, and they are opposite to each other, as it should be for a couple of enantiomers. Also, when Andrea did for the simulated IR-VCD experiments, if we superimpose the two, the experimental and the simulated one, those are quite good. So at this stage, we can conclude that the cluster is behaving like an enantiomer compound. But how can this chirality transfer happen? Again, Andrea did a lot of, qualitative DFT analysis for us. First of all, NCI in the surfaces, non-covalent interaction. You can see here in the green surfaces that we have this type of coordination that are van der Waals coordination type, and these are between the two terminal CO ligands in proximity, respectively, of CH2 and CH, so the chiral center of the cysteine. Second, the calculation of the critical points. First of all, we confirmed that here, with these two BPC, we have probably a covalent, a dative bond between the sulfur and two iron atoms. And also, we have found, again, an interaction between the same CO ligands and this CH2 of the cysteine with this RCP and BCP points. So with all these interactions all together, we can justify this chirality transfer. Lastly, if we look at the displacement vectors of the most intense band of the VCD in the simulated VCD, the most intense band is this one in negative band. We see that the displacement vectors are placed, belongs mostly to these two CO ligands, terminal CO ligands that in fact were the one in the slide you have seen before, coordinating, interacting with the chiral center and generally with the cysteine. So again, this confirms this peculiar ligand to cluster chirality transfer. Just a final summary. So we started from the oxidation of our precursor, iron 6 carbide 4- with the retention of the cage. Then we have tried to oxidize in the presence of a trapping agent, enabling substitution with these ligands, simple ligands. Then we conducted IR spectral electrochemistry and DFT studies to better understand the mechanism and the intermediates involved. Then we have the lab developed this procedure of functionalization of iron 6 carbide organic sulfur cage. And lastly, we expanded this study and synthesized this iron 5 carbide cysteine cluster, which exhibit this very peculiar ligand to cluster chirality transfer. So that was all from me. Of course, I want to thank the lab group, my professor, my colleagues, the committee for having me today, and you for your kind attention.
Thank you, Francesca. Very nice presentation. Any question for Francesca? No? I have one. Just a curiosity. I saw that your case is stable in the presence of this rigid phosphine, but not when you had the triphenyl phosphine, right? Did you try other phosphine with a different basicity? Or yes?
No, in this case, we haven't tried because at that point of the study, the main aim was achieving the functionalization without the breakage of the cage. So we were not into testing all the phosphines, but to, expand the study and then arrive towards the point to use organic sulfur ligand. So in this case, no. Thank you.
Okay. Thank you again, Francesca. So Francesca was the last speaker of this session, so I would like to thank again all the speakers of this session and about all you for so interesting discussion. Bye.
And everything will be done, but this very simply click here, but there is also a lady that helps.
Okay. Good afternoon, everyone. I'm Christian Ehm from the University of Naples, and I have the pleasure and the privilege to introduce the last speaker at this wonderful conference, Professor Capacchione. He hails from the University of Salerno, where he received his PhD under the tutelage of Antonio Proto. He is the recipient of a prestigious postdoctoral fellowship from the German Humboldt Foundation, where he worked in a group of Lutz Grade at the University of Heidelberg. And when he returned to Salerno, where he is now a full professor since 2021, his research interest centers on the field of stereoselective polymerization, promoted by transition metal complexes, homogeneous catalysts with a focus on valorization of bio-based feedstocks and carbon dioxide, and sustainable catalytic processes. His talk is titled The Second Life of Homogeneous OSSO Titanium Catalysts from Fossil-Based Monomers to Stereoregular Polymerization of Terpene-Derived Monomers. And without having heard a single word of what he's going to talk about, I already appreciate the play on 2 of the 5 R's: reuse, repurpose. And without further ado, Camino.
So first of all, thank you, Mr. Chairman, for your kind introduction, and also I would like to thank the organizing committee to give me this opportunity today to give this lecture, this last lecture of the Congress. So my story start this one. Start with the poster of cinema. So this one is a famous movie of Alfred Hitchcock. Title is Vertigo. I think many of the oldest of you, I'm sure you know. The young, I just say something. It's considered one masterpiece of Alfred Hitchcock, and the original title was Vertigo because James Stewart, the male protagonist, suffered post-traumatic acrophobia, so the fear of heights, and the female protagonist is Kim Novak. So the original title, so this one is the original poster, and the original poster is Vertigo. So we like to change completely the title of the movies from the English version, and the Italian one is the La donna che visse 2 volte, so the woman who lived twice, because also in the plot Kim Novak has 2 different identities, and this thing happens quite often in chemistry. So there are a molecule that is thought to do something different. And I will tell today the story of this one that was synthesized for the stereoregular polymerization of olefins and dienes, and then I applied for the synthesis of bio-derived monomers. So just a bit of story. So the stereoregular polymerization start with the discovery of the Ziegler catalyst. Actually, this one is not stereoregular, but is the key for the stereoregular polymerization. The guy who achieved the stereoregular polymerization of polypropylene was Natta, and this was the time of the development of the plastic industry based on these processes. Then after so many years, there was not much science about the Ziegler-Natta catalyst except the industrial development. In the 80s, Kaminski discovered that these molecules, this product in the MAO combined with the metallocene can give a high molecular weight polyethylene with activity comparable with the heterogeneous catalyst. Then the story moved to the stereoregular polymerization of alpha olefins by using ansa-metallocene developed by Britzinger and used by Ewing and Britzinger, and it was possible to achieve a very high level of sophistication by controlling the symmetry of the catalyst, some substituent controlled the molecular weight. So it was a very mature catalysis that developed with many rule that was possible, for example, obtain highly isostatic polypropylene, symbiotic polypropylene, elastomeric polypropylene. Then in the last decade of the last century, there were two development in this field. One is the development of homogeneous catalysts with the late transition metals, mainly from Brugard, Gibson, and Grubbs, nickel, and iron cobalt complexes. And the other one was development of alternative ligands than metallocene for the group 4 catalyst. I just reported the two most important discovery from Moshe Kohl and Fujita and Coates group that are based on Salen and Salan tetradentate ligands that was possible to obtain the selective polymerization of propylene. So we just divide this the story of homogeneous stereoregular catalysts in 3 eras that are the heterogeneous Ziegler-Natta, the metallocene, and the post-metallocene. So if you look at the catalysts that I have shown, all mainly are based on Salen or the reduced version on Salen, that in this case it's possible to change the R1, R2 substituent, also to change the length of the bridge. There was this kind of ligand were studied in many kind of catalysis. Then we introduced these new ligands, substituting the 2 nitrogen with 2 sulfurs that are soft donor and can give to the metal center different electronic properties. So we studied this ligand with the many metal centers, so with the zirconium and the titanium, hafnium in our group, and also in the group of Okuda with vanadium, scandium, yttrium, aluminium, indium. We also developed in the last year iron and chromium for the copolymerization of CO2 with epoxide and the copolymerization of epoxide with cyclic anhydride. So it was also a very successful class of ligand. And in particular, these 2 complexes were very versatile for the stereoregular polymerization of many olefin monomer. In particular, this one is the only soluble catalyst based on titanium to give isostatic polystyrene. Also, we achieved the stereoregular polymerization of butadiene and isoprene, the copolymerization with styrene, the isostatic polyformethyl. Oh, sorry. Can I back? Okay, of 4-methyl-1,3-pentadiene, and also the copolymerization with ethylene of other diene, and also the stereoregular polymerization of 1,3-pentadiene. So if you look, it's very versatile with the diene and the styrene-based monomers. So the one class of natural molecules that is potentially very interesting in this for the obtaining of polymer are terpene and terpenoids. So terpene are the molecules that not contain heteroatoms. Terpenoids also contain heteroatoms, and they are ubiquitous in nature. They are present in many essential oils. In particular, so there are the simplest one that, like myrcene, it's composed by 2 isoprene units, and then there are higher terpenes. One source that is very economical of terpenes is the turpentine, that is the volatile part of the pine resins that can be obtained substantially like the natural rubber. So the turpentine is very rich in these 2 molecules, and these 2 molecules by pyrolysis can give very easily the formation in high amount of myrcene. So we started from these sample molecules, myrcene, and when we started from this, the polymerization of these molecules, there were already some examples. And you can see that all the catalysts are based on lanthanides, lanthanum, lutetium, and other lanthanides, and give also, in this case, some stereoregular polymerization of myrcene with 1,4 trans, 3,4 trans isostatic. In this case, you can see, depending from the metal center, you can obtain a different taticity. So we tried our catalyst with myrcene, and what we obtained, you can see that depending from the substituent, so with the more bulky Q-mix substituent, we have a low control of the polymerization, the stereoregularity, while in the case of the compound with the therapeutic, we have a very good control of the stereoregularity with the ATG that you can see it's under ambient temperature, that is the first requisite for the application as elastomer. So then we moved to osimine, that is another monoterpene that has a different structure, and also in this case we observed some interesting thing. You can see that if we perform the polymerization of high temperature, we don't observe a very high control of the stereoregularity. If we lower the temperature at room temperature, you can see that in this case you have a much better control of the stereoregularity with the prevalently 1,2 structure of the polymer. So this is evident by performing the polymerization of 90 degree and 0 degree. You can see the spectrum is completely different. This one was it's clearly a highly stereoregular polymer with the 1,2 stereochemistry, and it's also isostatic. So we have evidence in this spectra that you, depending from the temperature, you can obtain completely different polymers. Then we move to copolymerization with styrene. That is also possible to obtain with a very large range of composition and with a high degree of incorporation of styrene. And again, depending from the composition, you can obtain a very low TG, and let me say also a good value of molecular weight. We characterize these copolymers by NMR, and depending from the composition, you can see that it is evident that at low amount incorporation of styrene, the styrene is mainly present as isolated units. By increasing the amount of styrene, there are also some small block of polystyrene in the copolymer. We also copolymerized osimine, and again, also in the copolymerization, there is a temperature-dependent behavior. At high temperature, you can see that we have a low control of the stereoregularity in the osimine part, but at lower temperature, in this case at room temperature, you have a good control of the stereoregularity. But you see, in this case, the TG increase, and you cannot think to apply this polymer as an elastomer because, of course, the high stereoregularity in this case cause an increase of the TG. Also, of course, this is evident from the NEMA spectrum. This one is the polymer with at high temperature, this one at room temperature, and you can see the spectra are completely different with different stereochemistry of the osimine blocks. We also extended the copolymerization of myrcene with butadiene. In this case, we obtained again very low TG, and that it's possible to apply as an elastomer. Also, a high degree of controlling of stereoregularity, not so high, but sufficient to have a good molecular weight. Also, osimine we copolymerized with butadiene, and also in this case we obtained copolymer in a wide range of composition with good thermal properties. We also tried to obtain terpolymers, and what we observed in this case, you see that in this case, the catalysts just differ from this remote substituent. In this case, we have the cumyl group on the parallel position. We have the same group on this position, but with the methyl in this position. And in this case, what we observed, that we observed that in the case of the catalyst 1, we obtained lower molecular weight. And in the case of catalyst 2, we, in the same, exactly under the same condition of feed and temperature, you obtain much higher molecular weight. That is important to have to increase the molecular weight for the application. So until now, we see these catalysts are very versatile. You can obtain different stereochemistry of the polymer, but there is a chance to apply this polymer for something useful. So we were able to polymerize in macro sample. So that means 500 grams of polymer on laboratory scale. And you can see that we can obtain all copolymers of ocimene with butadiene and also terpolymer with ocimene, butadiene, and styrene in large amount. And we employed, in collaboration with Pirelli Tire, this polymer as resins, because you see that basically in a tire compound, there are many components. The main components are, of course, natural rubber, styrene butadiene rubber, and also there are filler like silica and carbon black, and there are, it's like a recipe. There is no much science in the tire compound. There are a lot of components. It's not clear which component is the role of each component, but you can see that they use these resins that are usually thermoplastic, that are used to increase the thermal property of the compound. So what we made in collaboration with Pirelli, we substituted these resins with our polymers. And what we observed, that in the case, you see, we have three different compounds, one with our polymer, one is the Pirelli patent, and one is a commercial compound, that you see can, in any case, the compound containing our copolymer has better mechanical properties, stress at break, elongation break, and also the property like tan delta and E1 that are fundamental for the behavior of the final compound as dire that give some useful information. This compound was patented from Pirelli, and now we continued to study these monoterpenes, and very recently we obtained the copolymerization of myrcene with ethylene. I just show you in the past that was possible to obtain this structure with the cyclopentane unit by using alpha-metallosine. With the lanthanide, they obtained a mixture of 1,4 and 3,4 structure with the copolymerization. With this earth-abundant catalyst, our titanium catalyst, it was possible to obtain a much higher stereoregular polymer, up to 95% of trans 1,4 microstructure. This copolymer were characterized. Also, I also show that it's possible to obtain in a wide range of composition, and we observed a TG that is fundamental for application as elastomer, very low also in the copolymerization with ethylene. So surprisingly, the TG lower by increasing the amount of ethylene, because there are no homosequences. Then we moved to another terpene that is derived from the citral that is contained in the essential oil of citrus. This one can be easily converted by Wittig reaction to these molecules, the dimethyl 1,1,3,7 nonatrene, and we employed this molecule in the homopolymerization and in the copolymerization with ethylene and styrene by using the STU also catalyst. So what we observed, the polymer is highly isostatic with high regioselectivity, with good molecular weight, the homopolymer, and it's also possible to obtain copolymer with ethylene and styrene with the two, and in the case of styrene, it's also possible to obtain a block-like polystyrene poly-DMNT by sequential polymerization. So the thermal property are shown in this case. The copolymer with the ethylene remain elastomeric with the low TG. The TG increase in the copolymer with the styrene, and also block copolymer. You can see that show dual TG, one of the DMT block, one of the styrene block, and in this case you can observe also the melting transition of the highly isostatic polystyrene. So we also did some post-polymerization reaction by epoxidation of this double bond, the dependent double bond that was achieved in a good with good yield, and we performed some water content angle of the epoxidized copolymer. So evidently the introduction of epoxy would provide a versatile platform for further functionalization, and also significantly reduce the water contact angle. You can see that there is a sensible reduction of the copolymers with ethylene and styrene, the block copolymers in all cases of the water contact angle, meaning that the epoxidized copolymer are much more hydrophilic. Then we moved to this molecule, this vinyl cycloisine, that is not derived from terpenes, but serve as a platform from to study as model molecule to study the polymerization behavior of cyclic terpenes, because we studied, I showed up to now only linear terpenes. We moved to cyclic structure, and in this case, what we observed that in the case of it was reported the anionic polymerization give a mixture of 1,4 and 3,4 units, and the group 4 metallocene give 1,4 cis unit. Only one case with the very low activity that was reported, the stereoregular polymerization. We obtain highly isostatic polymer, homopolymer. This molecule is obtained by hydrogenation of the alkene. So, and then we moved to natural occurring polymer that is derived from this perillaldehyde that is from the plant Perilla. By Wittig reaction is possible to transform in this molecule. And we isospecifically polymerized both molecules, this one and this one. You can see that the isospecific very high, good molecular weight in both cases, and narrow polydispersity. And you can see that TG in this case is very close to the TG of polystyrene. What was very interesting, we found with the group of Professor Sauriem in Naples, that it's very strange. This polymer, if after annealing show no crystallinity, so then we hydrogenated this polymer to obtain this polyisostatic vinyl cyclohexane, and what we observed that changing, just hydrogenating this double bond, you pass from a amorphous polymer to a crystalline polymer. This one was reported, the spectrum, the X-ray spectra of this polymer. So the polymer morphology changed just by introduction this double bond on the side chain of the polymer, and you can see that both polymers from NMR are really highly isostatic. So it's not due to the low isostaticity of the polymer, but is due to the presence of this double bond. So we polymerized this derived from perillaldehyde with osmium and myrcene in order to obtain some completely biomass-based copolymer. This way, the TG is higher, but still we can obtain by regulating the composition of the feed some TG that is lower than ambient temperature. And also we copolymerized with the DMNT by introducing with this monomer, and you can see also in this case the different thermal behavior of copolymers containing different amount of the copolymer. Finally, we also studied the stereoregular polymerization of these molecules derived from the cinnamaldehyde that is usually obtained from the essential oil of many kind of cinnamon. This one can obtain again with the Wittig reaction in good yield. Was reported the stereoregular polymerization with the low stereoregularity with the monocyclopentadienyl titanium complex, and we also with the nickel complex. And much more recently was reported the highly symbiotic and regioregular polymer obtained with this lanthanide catalyst. And you can see that the value of TG of this homopolymer is relatively high. What we observed with our catalytic system, so we observed that in our case, we obtained very high isotoxicity, so 3,4 is high regioregular and also highly isospecific, is isoselective. The reaction at 80 degrees, we have the maximum of activity. We have a good conversion after 24 hours, and it is evident that it's an isotopic polymer because you can see we can observe the NMR spectra. This one is the proton spectrum, and you can see that the two proton A and B are showing a typical AB pattern, and also you can see the carbon spectrum is also very, there are very sharp signals indicating the obtaining of very high isotopic and regioregular polymers. We also copolymerize this monomer with the other biomass-derived monomers, and it's also in this case possible to obtain the copolymer with a wide range of composition, again with very narrow molecular weight distribution and good molecular weight. Also with the DMT is possible to obtain a copolymer with phenylbutadiene. In this case, you can see that depending from the amount of EVC and phenylbutadiene is possible also in this case to regulate the TG of the obtained copolymers. So in conclusion, what we have shown that these catalysts are also sustainable catalysts for polymer innovation. We employed the titanium complex. There are earth-abundant catalyst metal for the efficient and stereoselective synthesis of novel polymer from fully bio-based monomers. These polymers are unique microstructural feature. There are in some cases have also I didn't show this polymer, but also tunable glass transition temperature, enabling low temperature elastomeric application, incorporation and post-functionalization of external double bond, because in the case of terpene, you can have some double bond on the side chain of the polymer that can be further functionalized. There is a high degree of the control of the polymeric architecture by the possibility to obtain block and multi-block copolymers and also random copolymers, overcoming the challenge of different monomer reactivity. And of course, this one is only I hope the beginning of the story, because there are also many other possible monomer too can be polymerized by the systems. Finally, I would like to thank all the people from the University of Salerno working on the project, especially David Lamparelli, Ilaria Grimaldi, and Assunta D'Amato and Maria Rosaria Gambardella present here. The University of Naples that did all the work of characterization with many polymer. University of Mainz, I didn't show this result. In the last time we started the collaboration with the Professor Frey to obtain some data on kinetics. Of course, I would like to thank the Italian Ministry of University, Pirelli, and the Alexander von Humboldt Foundation for financial support. And I would like to thank you, all of you, for your kind attention.
Thank you so much. Sorry. The contribution is open for discussion, remarks, questions. Anyone? Maybe I start. Your catalyst 2, as an organometallic chemist, I appreciate the fact that you can tune. As a computational chemist, I shiver at the fact that this thing probably has 6 times more transition states. And as an data scientist, I'm just questioning whether I could ever featureize this. The reason is, of course, that it's a simple CC rotation away from a C1 symmetric species. Do you have any insights whether the errors are introduced by a C1 symmetric species?
You mean that from C2 symmetric you change to C1 symmetric?
Through the rotation of one of the substituents in auto position.
If you have a substituent smaller than terbutyl, you observe on the NMR timescale the rotation of the system. If they are from terbutyl to Eiger, so you cannot observe any interconversion between C2 and C1 symmetric. This one was documented long time ago, and also when you have a rigid complex, they are active in polymerization. If you have a fluxional complex, they are completely inactive in polymerization. Just if you change in the ortho position from terbutyl to isopropyl, so you completely lost the catalytic activity.
Okay, thank you.
Thank you very much. I just have a very general question, because now there is this trend to more sustainable plastics. And so that's in this area, because you're using renewable monomers. But what about in terms of degradation? Is there any increased biodegradability or depolymerizability of these materials relative to other plastics?
In this case, is a class of bioplastic that is only biomass based. So we don't have particular feature to have a biodegradability at the end, because we have a lot of double bond in the final polymer, and of course the double bond favors the decomposition, but they are not particular. So I think in the field of biodegradable polymer, the main role is from polyester and polycarbonate. This is now basically polyolefins. It's not one feature that I can stress of these polymers.
Okay, then let's thank Carmine again. And I think it's time for the closing remarks, but if you can spare an applause for the organizing committee and the scientific committee. Thank you.
Va bene, grazie. Siamo arrivati alla fine di questa magnifica conferenza, è stato davvero un piacere e adesso arriviamo a un momento però che è altrettanto che il clou è veramente importante, perché premiamo i 3 migliori poster e la migliore presentazione orale. I premi sono, come dire, vengono erogati grazie al contributo della Royal Society of Chemistry attraverso i giornali Dalton Transaction e Crystal Engineering Communication, e per una volta sono dei premi come dire, diciamo, non cospicui, che però insomma sono 100 euro per ciascun vincitore di poster e 200 euro per il premio alla migliore presentazione orale. Dico solo una nota tecnica: i vincitori o le vincitrici per favore contattino via mail la professoressa Barbara Milani per avere poi il bonifico, i dettagli. Allora, questa conferenza, come all'inizio avevo detto, no? Diciamo, è l'occasione per condividere i nostri lavori, ricerca e quant'altro, e dare l'opportunità, come dire, di mostrare come la chimica inorganica italiana sta avanzando e lo sta facendo in maniera veramente notevole. Diciamo, siamo rimasti tutti diciamo, veramente colpiti dalla qualità davvero elevata delle presentazioni e dei lavori che sono stati presentati, in particolar modo dai più giovani, e questo credo faccia la differenza. Dagli oratori più senior ci si aspetta una bella presentazione, dai più giovani diciamo, vedere un grado così elevato di qualità nella presentazione, nei risultati, non è banale. Quindi per questo davvero io e tutto il direttivo si complimenta con voi, e naturalmente ci avete dato dei grattacapi, perché scegliere i migliori poster e la migliore presentazione orale non è stato per nulla facile, ma insomma alla fine una scelta andava fatta, e quindi adesso annuncio i vincitori del premio poster. Quindi il poster indicato come P19, presentato da Felicia Daniela Cannavacciuolo dell'Università di Napoli Federico II. Sei in sala? Vieni. Ecco qui.
Grazie.
Molte congratulazioni.
Grazie mille. Ah,
Otto?
sì. Grazie mille.
Il secondo premiato, naturalmente sono premi ex aequo, è Giuseppe Sportelli dell'Università di Trieste. Congratulazioni. E Jennifer Storchi dell'Università di Modena e Reggio Emilia. Ecco qua. Congratulazioni. Adesso premiamo la migliore presentazione orale, che è stata fatta da Maria Edith Casacchia dell'Università dell'Aquila. E beh, vede che insomma, complimenti. Va bene, quindi io vi ringrazio davvero, vi do appuntamento alla prossima conferenza a Torino, ma adesso passo la parola a Francesco Ruffo per la chiusura ufficiale di questo congresso. Grazie.
Allora, siamo giunti alla conclusione. Prima dei saluti però alcuni doverosi ringraziamenti. Il primo e a tutte voi e tutti voi che siete venuti a Napoli. Siamo quasi 300, 45 sedi rappresentate e in particolare voglio ringraziare i giovani che hanno partecipato molto attivamente al convegno con delle presentazioni eccellenti. Abbiamo scelto questa sede impegnativa e prestigiosa e ringraziamo anche l'Università di Napoli Federico II perché i giovani possono portare a casa questo ricordo, questo scorcio di Napoli così soggettivo. Ovviamente auguriamo di poter coronare tutti i loro sogni e di mantenere viva questa passione che hanno mostrato. Poi voglio ringraziare le persone che non sono venute, che non sono potute venire. E tante mi hanno scritto, hanno mandato delle email esprimendo il rammarico per la loro assenza. Un ringraziamento molto sentito a tutti quelli che hanno partecipato attivamente all'organizzazione di questo convegno. E senza far torto a nessuno, devo esprimere la mia riconoscenza autentica a Daniela e a Narita, che vorrei vicino a me, che sono due compagne di viaggio insostituibili e anche angeli custodi, devo dire. Annarita, io e Daniela veniamo da 3 dipartimenti diversi. Annarita agraria, Daniela farmacia, io scienze chimiche, e questa diversa provenienza ha fatto risaltare ancora di più la molteplicità della chimica inorganica napoletana, la possibilità di lavorare in modo coeso, e speriamo che questo si riverberi in futuro anche coinvolgendo le altre università campane che hanno contribuito all'organizzazione del convegno, in particolare la Vanvitelli, Salerno, l'Università del Sannio, che ringraziamo di cuore. E un ultimo ringraziamento voglio farlo a Napoli, che ci è apparsa con tutti i suoi colori, l'azzurro del bel tempo, il grigio della pioggia uggiosa dell'altra sera, e soprattutto perché ha mantenuto sopiti i bollori del sottosuolo. Anche perché, diciamocelo, quel gigante che sta qui dietro la curva non è qui per minacciarci, ma per proteggerci e sicuramente per augurarvi un buon ritorno a casa. Grazie ancora.